Mhm. Okay. Will they go soon? I think they are not ready still. Prepare something. It will be good if all students can. This material, this result should be very useful for people interested in generalized inverses, for people interested in numerical linear algebra. Are we ready? Okay. In this lecture, I'm, I will present you some results published in this paper. It was paper published in Journal Complexity 2017. Why I want to explain just this paper? Because in this paper we introduced one unique approach in computing generalized inverses. This approach is based on two steps. First step assumes solving particular linear matrix equation. And in second step, we will exploit solution obtained in step 1 and multiply this solution from left and or from right, and in this way obtain wanted generalized inverses. So this approach is specific in case because it is not kind of direct methods, not kind of iterative methods. It is based on one specific algorithmic framework. Solve particular linear matrix equation, and in second step, exploit solution of this linear matrix equation and obtain corresponding G inverse. Here is first result. This result presented in theorem 4 here contains two parts. First part gives a representation of generalized inverses. Second part enables practical computational algorithm for generalized inverses. Particularly, this theorem is aimed to computation of outer inverses satisfying prescribed range Such G inverse, one example of G inverse will be denoted in this way. Outer inverse with range R of B. B is given matrix. Here is star, which means we are not interested in null space. We only want to define range of outer inverse. Class of outer inverses with prescribed range R of B is defined as set of matrices X such that XAX equals X and range of X is equal to range of B. It is class of outer inverses with prescribed, with predefined range, and there is one particular outer inverse with prescribed range. Of course, we can consider outer inverses with prescribed null space in analog way. If we consider outer inverses with prescribed both range and null space, what will be? How many elements then we will have? Then we will have only one element, because such outer inverse with prescribed both range and null space is unique. It is in relation with well-known BC inverses. This theorem 4 is aimed to computation of outer inverses with prescribed range. Null space is not defined. Can be, but we are not interested in this moment. We want only to precise range of such outer inverse. And in first part of theorem, part A, we gave 5 equivalent statements. Part B gives useful representations of such outer inverses, and after such representation we can propose appropriate algorithm for computation of such outer inverse. I will present paper published visible. Here is this theorem, theorem 3. First equivalent condition is exists two inverse of X satisfying range of X equals range of B, and we denote such inverse as we spoke previously. Second condition, exists matrix U of appropriate dimensions, of course, such that equation, matrix equation BUAB equals B is satisfied. Condition 3, statement 3, how can we read? Null space of AB is equal to null space of B. Ranks of A, B, and B are equal. We know in advance that such two conditions, 3 and 4, are equivalent. Condition 5, statement 5, equation BAB1 AB equals B is satisfied for some equivalently every inner inverse of AB. Why some or equivalently? If this equation is solvable for arbitrary one inverse, will be solvable for one inner inverse, AB1 will be satisfied for arbitrary inner inverse. Second part gives a representation of class of outer inverses with defined range. And according to this representation, later we proposed a corresponding algorithm. Proof is really, how to say, specialty for people who like mathematics, and it is one algebraic approach. It is one combination of numerical linear algebra combination with algebra, usual algebra, in combination with computer science, after all. Condition 1 exists outer inverse with prescribed range. 2 exists matrix U of appropriate dimensions such that BU AB equals B. How to prove 1 implies 2. In this proof you will recognize pure algebra. Assume existence of outer inverse with prescribed range. Denote it by X. It means that equations XAX equals X is satisfied, and range of X is equal to range of B. According to equality of two ranges, we obtain one general form of X given as product BU. Such a representation means that range of X is subset of range of B. Why? Because X is product of B times something, and each value that we use for U, BU must be from range of B. But we have opposite inclusion. B can be represented in form WX. Opposite, we will use xw range of B equals to range of x. X first, range of B, range of x. Range of x equals range of B. Then, for some matrices U and W, then B is equal to xw equals to xaxw, because it is true, because matrix X is outer inverse of A. xw is B. Here is equation xab equals B from for BC inverses. Equals. Now we will write BU instead of X and obtain equals BUAB. Here is equation, matrix equation. BUAB is solvable. One interesting implication: existence of outer inverse with range, and then such matrix equation is solvable. Exists U, which is solution of this matrix equation. We need to verify equivalence of several conditions. We verified 1 implies 2, then 2 implies 3. No enough space, 2 implies 3. We suppose existence of U such that BUAB equals B. Inclusion, null space of B subset of null space of AB is evident. It is well known. Because when value of B gives 0, AB will be also 0. We need to verify opposite inclusion. Null space of AB is subset of null space of BU AB. Of course, AB, here we have BUAB, but BUAB is equal to B. It is null space of B. So, null space of AB is subset of null space of B. Opposite is evident. And it means null space of B is equal to null space of AB. And immediately we know that ranks of A, B, and B must be equal. Ranks must be equal. Do you remember our assumption rank of GA equals to rank of G. In dual case, we will have rank of AG equals to rank of G. Here we can see meaning of this in details. Three and four are equivalent. And we need to verify five. 3 implies 5. 3 and 4 are equivalent, so easier was in that moment to verify 3 implies 5. I must remove something. Statement 3 says null space. Again, I will say or ranks are equal. It means we can find matrix V of appropriate dimensions. Then it is equal to see this identity. Why this? Evidently, because here is inner inverse, it is equal to AB. Now we will replace VAB by B and obtain BAB. 5 implies 1. Our is satisfied for some selected inner set x equals to then we have AX equals to B, AB, new X, B, AB, 1. It is equal to B. First, watch this identity. My first impression was it is wrong. It is not our outer inverse, but this equality between inverse. It is because of equation B. AB1 is equal to AB1, AB is equal to B. It is equal to X. We we have rank of AB is equal to rank of B because of equalities of null space. And then BAB1AB is equal to, it implies BAB1 AB is equal to B. And because of that, here we have BAB1. So matrix equation XAX equals X is satisfied. And then it will be necessary to verify second part, representations arising from equivalence described in first part. Part B. Now we consider set of outer inverses. It is subset or equal to such that BUAB equals B. And according to rank equalities and this equation, here we can conclude U is one inner inverse of AB, multiply from left by A, ABU, AB equals to AB. We have rank equalities. It is subset of B, AB1 such that, of course, it is not necessary to write AB1 is inner inverse of AB. And we verify that it is subset of what is conclusion after this result. Consider this equality 5. Set of outer inverses with prescribed range is given by BU such that BUAB is equal B. This identity set identity 5 is most important, and gives practical algorithm how to compute outer inverses with prescribed range. This equation is important. Finally, we know that U is one inner inverse of AB, BU, such that BUAB is equal to B, or B equals BAB1. Outer inverses. Outer inverses are generated using inner inverses. If we use all inner inverses, we will obtain class of outer inverses. Class of inner inverses is generator of class of outer inverses. Outer inverses with inner inverses, but next relation is algorithmically applicable. Linear matrix equation BUAB equals B. In step 2, compute x equal to BU. Only 2 steps. It is practical algorithm how to compute outer inverses, solving and such approach rings, semi-rings. For such approach, and for quaternions, solve matrix equation. It is general for outer inverses with prescribed equation BUAB equals B. This equation is solvable if this condition of equal ranks is not satisfied. This equation will not be solvable. Here in this paper, we used gradient neural network to solve matrix equation. Here is it all methods are open. You can use iterations, you can use arbitrary method which you can propose and solve this matrix equation. And later in second step, only multiply solution U by B from left, and it will be our outer inverse. Here we used, we can analyze this model. Of course, we BU AB equals B. How will we model? Do you want BU AB minus B? It will be our error function E of t. B. It will be our error function E of t. And according to this, such GNN model is developed. Numerical linear algebra and computer science all started from, then we used in matrix theory, and finally recurrent neural networks to solve problem. V of t is there. No? V of t. And it is one specific way how to find approximation function. Frobenius norm. 1/2 Yes. Okay. Then derivative of epsilon with pose v of t ab minus b, and then because but b and ab transpose dot v from left time derivative papers with hard theory then algorithm interesting for reviewers and for publication. Minus gamma, yes. Y gamma. Minus when we use nonlinear activation function. The linear model is also convergent, globally convergent. And use matrix B satisfying rank of AB equals rank of B to find algorithm. Here is use matrices A and B, check rank conditions. If these conditions are not satisfied, stop. We will not obtain equals B, and then return outer inverse. Obtain outer inverse. Outer inverse of rank equal to rank of A is reflexive inner inverse, is one inverse. Algorithm for outer inverses, we can obtain corresponding algorithm for reflexive inner inverse. Only we will consider particular subset of outer inverses. A lot of algorithms, we will have a lot of particular cases. If we consider all cases, it will spend time varying matrices A and B, verify rank of AB equals rank of B, solve BUAB equals B with respect to U, rank of AB equals rank of B equal rank of A. Here we will obtain in BU 1-2 inverse with prescribed for 1-2 inverse. How to solve this matrix equation? As you want, you can use different algorithms. Here we proposed gradient neural network approach. Probably for in that time we were experienced only in a gradient neural network. And of course, zeroing neural networks are applicable also. And here is B input. It is our input. And then we go step by step. AB, ABU, AB, B, AB, B is here first, U is output of integrator. Here 1 by S is ODE solver, which will solve system of differential plus, minus b. Here we will trace norm of residual matrix. It will be residual residual function. What is here? It was pure linear activation function, and here is one of nonlinear activation functions. If we make double click here, we will see which activation function is there. Power sigmoid, smooth power sigmoid can be. Double click on this switch will give choice between linear and nonlinear models. Here BU, A, B minus B. We need to multiply by AB transpose. Because of that, here we prepared AB transpose. There we prepared B. It is what? Gamma, gain parameter. Here we can define gamma parameter. Here is. And solver. This we can consider it as V dot integrator U dot, okay, integrator will return U, and then next time instant until the end of our time interval, and then output. In output we decided to present in display blocks values of BU and value of U and BU. Why we used to present value of BU? Because what is BU? BU is our outer inverse with prescribed range. Thank you. Then their proposed null space. Then outer inverse, not inverse, is outer inverse with prescribed both ranges. Here is dual result for outer inverse. With prescribed null space. Then exists appropriate matrix U such that range and null space. We need only for null space. Here is exists outer inverse with defined null space denoted in this way: star, comma, null space. Star means we are not interested in the range in our case. CAV, C equals C is satisfied in this case. If we multiply right from A, we will see that matrix V is if we have CAV, CA equals CA, matrix V is inner inverse of CA, same, and matrix equation CA, CA1, C equals C is satisfied. Such equation is satisfied if and only if rank of C is equal to rank of CA. And then in part B we obtained corresponding representations. Is VC such that CA VC equals C satisfied. If we change solutions, we will obtain different outer inverses with the prescribed null space. Theoretically is important result in first row of 12 because this result relates outer inverses with prescribed null space. And the corresponding result for BC inverses is practically corollary of these two equations, but there was some only corollary, because in this case we have solvability of two matrix equations. One is BU CAB equals B, another one is CABVC equals to C. And if one of these equations is solvable, another one is also solvable, and results are the same. Finally, BC inverse, outer inverse with prescribed both range and null space is unique. Rank of CAB must be equal to rank of B equal to rank of C. If we continue here and put equal rank of A, what will we obtain? Ask more, ask here equal rank of A, then we will obtain 1, 2 inverses. Always outer inverses give 1, 2 inverse when we consider case with rank equal to rank of A. Yes, we have solvability of two equations, and if one of these two equations is solvable, another also is solvable, and the solutions are equal. Numerical results say it is not absolute identity because of numerical calculations, but results are the same, numerically equivalent. And then we have BU equals VC. We can use one of these equations. If we use first equation, we can multiply by B from left. If we use second equation, CAVC equals C, we can multiply by C from right, but result will be the same. The result will be the same. Okay. I think we exhausted your time. You can ask some questions. For all cases, corresponding GNN models are developed. Corresponding GNN models. The GNN models were applied for polynomial matrices. If you want. Shabaum ZNN models can be used to solve these matrix equations. It is possible.
So for the time varying matrices, can we use the same architecture to and expect the good results?
if we use time varying matrices, ZNN is known as better. I spoke that in that time we were 2017, research started in 2016. We were familiar only with GNN and applied GNN for time varying case and worked. Yes. Probably examples which we consider were appropriate and GNN solved this problem. Such GNN models applied to time varying cases are called generalized GNN, GNN. Of course, it is possible and better to use ZNN, not developed so far. Possible, it is possible to work. Prepare ZNN to solve corresponding matrix equation and then multiply. Or propose another algorithm to solve matrix equations.
Can we combine ZNN and GNN?
Can. Can be. We will combine GNN and ZNN here. GIAN pose A plus I in front of nonlinear activation. And in that way, we will increase, how to say, improve, we will improve GNN or will improve ZNN. It will be question next week. It will be next week.
Okay, thank you.
Is it difficult?
Sir, here
Difficult.
AB equal to rank of B to compute U.
Rank
First.
of AB must be equal to rank of B. Otherwise, model is not applicable, algorithm is not applicable. Rank of AB equals rank of B is requirement even for in theoretical statements. If you remember, here is this case. Theory requires and numerical experience requires also theorem 3. One of the requirements is rank of AB equals to rank of B. If not, nothing. Rank of AB is equals to rank of B. But it is not drawback of GNN model. It is drawback of linear algebra. It comes from results in numerical linear algebra. But I think it is possible to try with GNN, even this condition is not satisfied. We will obtain some results.
Here we find the 2 inverse with respect to range separately and with respect to null space separately.
What? When we
2 inverse with respect to
apply
range.
algorithm and compute outer inverse with...
Why didn't you use 2 inverse with respect to range and null space at a time? Means
if we want algorithm aimed to computation of only out, we will need rank of AB equals rank of B if we ask equalities of these two, we will obtain outer inverse if we use assumption rank of CA equals rank of C, we will it will lead to outer with range null space. In all cases, if we ask future equal to rank of A, we will obtain 1-2 inverse. We will obtain 1-2 inverse. So we have two dual algorithms. One is applicable in this case, rank of AB equals rank of B. Another one applicable in case rank of CA equals rank of C. Solve one of two possible equations, and result will be the same, if you can. Because outer inverse with both range and null space is unique. But if we have only rank of AB equals rank of C, rank of B, sorry, we can apply only one algorithm. If we have rank of CA equals rank of C, we can apply dual algorithm. Equations are different. Here is, can you help me? V which equation we will solve depends on rank equalities. If we have in both cases less, then both algorithms will not be applicable. Is it okay? Future questions? Okay. Safik looks, it's solved.
Okay. Good. Stop. Okay, thank you very much. Let's give big. Okay.
Oh, yes.
Yeah. Again, connect over here. Yes. Okay, thank you very much and good morning to all of you. Today we'll discuss and also I told you that QR is a stable decomposition, okay, but LU is not, okay. For that we have proved some result for the stability and which would be falling on unit round of errors and the floating point arithmetics calculations. So today we will discuss about the least squares and real least square problem and the SVD. As we have learned QR decomposition, in QR decomposition also we have used least square problem, how to solve least square problem by using QR decomposition. Similarly, we can see some basics of singular value decompositions, and before that I will give you some highlights on the process would give you if you set of linearly independent set and you are normalizing, and finally you would be getting this we have computed okay, and the given transformation. By using that we have done this QR decompositions. Okay, be using the permutation matrix while calculating the QR decomposition. Say for example here, suppose if a matrix has full rank, the algorithm terminates after m steps. The result is decomposition is of this form. This pi is this permutation matrix, and this permutation matrix, it will take you as a pivot elements. If it is, they can swap this, and this Q is orthogonal matrix and R is upper triangular matrix. Okay. Now here, if here doesn't have full rank, say for example, if you don't have full rank, at some step will encounter tau I equal to 0. This tau I, if you remember in our last class, this plus or minus norm of x2, and in our last class we defined while calculating the reflector. Okay. And this occurs when all the entries in the remaining submatrices are 0, and suppose this occur after R step, and let Qi denote the reflector used at the step I. Okay. Now what we will get in if the matrix is full rank, and you will get this and the rank of this yeah, for the case of full rank we are already in our last class we have given, okay, rank is R, and this RH we will be getting the matrix which is non-singular and the size is R by R. Okay. And this diagonal entries of this RH would look like this tau 1, tau 2 and tau R, all non-zero entries, and the rank of R would be R. So here what we are doing that we are again and again applying the QR factorization, Q1, Q2 up to QR, and then you take the Q transpose, you will get this QR transpose. This is missing, this is typo, and the QR transpose, QR minus 1 transpose and Q1 transpose. So if you substitute this, you will get rank of matrix A equal to rank of R, and finally we will be getting rank of A equal to R. Now here you see, suppose you have this n by m, and this R is the RH and some non-zero, and this RH would be non-singular matrix. This is the statement of QR decomposition. Now we use this by solving this least square problem. As you have seen, this A is a n by m matrix, and we seek x that minimizes this one, infinitely many solutions. Okay, that we can see later part of by when this column pivoting. Say if you have the column pivoting, and say if A is the matrix, apply QR with this column pivoting, this A pi equal to QR, where Q is n by n the R by R, and is the upper triangular matrix, and it is non-singular. Here R is the rank of A and less than m. Okay, and pi is a permutation matrix. There are two things, row pivoting and the column pivoting. Okay, sometimes n is greater than m, or sometimes star here is R2 and 0 0, and here is of this form. Now you see how you are applying to calculating the least square solution. Suppose this say y equal to pi t x equal to this one, because you are just substituting QR, and here is it. And partition this y1, y2, where this R1, this is of size R by R, and the remaining this y2 is m minus R. So accordingly you are QTB, and 1 colon R means this is 1 2 up to R, 1 plus 1 2 3 up to R, and here 1 meter of this variable y1, this y1 dash up to y R dash. You will get this three variable. You can choose any y2 and it will work, and you can get infinitely such solutions, because y2 is a free variables case. And the x would be like this, R1 inverse, and this is 1 to R, and then it is a free vector Y2, and this up to this you have control. And so so we got this, it is like x equal to particular solution, and the solution which is satisfied in the null space, okay. And this is the dimension of null space is equal to m minus r, because this is the matrix R, and the remaining for the 0 variables, and this is the null space you will get, and this is size of this is this one. Now here you see there are infinitely many such solutions satisfying the minimum one, the one which satisfy the least square problem, okay, ax minus b nor, which is minimum x, okay. And as you see there are infinitely many solutions, you choose the a plus and b, and this is called Moore-Penrose inverse. So Moore-Penrose inverse you have seen, this is the solution you will get for which that x is minimum, and that solution is a plus this dagger R. I will discuss about the Moore-Penrose inverse later part of this. And a x minimum, this minimum solution, this would be the minimum. This a plus b is nothing but this one. So instead of calculating this a Moore-Penrose inverse from the singular value decomposition, so you can directly get from QR decomposition, okay, even if you don't, okay. And similar things we will see when we will study singular value decomposition, okay. Now there yes you can example A and B is the matrix, and this is maybe you can ignore this one, you just put QR in the bracket A, and you can put some tolerance here, and the sum of the absolute of diagonal of R is greater than tolerance. And that means say when you finding the numerical rank of this matrix, sometimes you have to define what would be the tolerance, after what you are choosing that 0, okay. In that case numerical rank it is telling, numerical rank, because up to which you want that, so you keep until this one, okay. And then you have this R1, you can extract this matrix, this is a 1 to R rows, and this is 1 to R columns. So you can extract from R1, this is R by R matrix, and then you can calculate this, and from here you can calculate y1 equal to R1 by b1. So this would be your unique solution y1, because R1 is and the size of a to 1 and xp is equal to y. So likewise you can display the x, the minimum norm solution. You can write this, discuss here about the classical Gram-Schmidt and the modified Gram-Schmidt process. As you have seen the QR decomposition by using reflectors and the rotators, and same thing you can find from the Gram-Schmidt process. Gram-Schmidt process is, if you have linearly independent vectors, then you can orthonormal, you can orthonormalize, and you can get Q1, Q2 of QM, and such that span of Q1, Qi equal to V1 into Vi, I varies from 1 to n. So with the process you are doing like this, as you can recall that Q1 you are getting on Q2, K2, 2 to m, and then you are finding this, all this. So all these multipliers we can write in the matrix form, and that matrix form you can get this. Say for example, all these vectors B1, B2 you just put as a matrix A, okay. And once you do this, then the Gram-Schmidt process from you can get A equal to QR. So where Q equal to Q1, Q2 up to Qm, whatever orthonormal vectors you got, that Q is this, and R is an upper triangular matrix. This R is, this is multiplier. So you just recall this RJK is the multiplier, because every time you are doing like this, say Vk equal to J varies from 1 to K, and RJK equal to this one, okay, where RJK is Qj transpose Vj, okay. So every time you are doing this, you are finding this V1, V2, V3 up to Vk, and then you normalize and you get the Q1, Q2, and so on. So if you write in the matrix say Vk, K varies from 1 to n, if you expand this V1, V2, V3 up to Vk, and if you write in the matrix form V1, V2 up to Vk, and this would be V1, V2 up to Vk, and finally you would be getting the QR. So gram scheme process also gives you QR decomposition. Of code is this QR classical gram scheme, and this NM, say size of this matrix A, and Q equal to zeros of n, start the process J equal to 1 to K minus 1, and you just multiply and you get this RK, and then you can get this. If you run this, and you can find the gram scheme process. Now compositions with different from gram scheme process. Also we can get some other orthogonalization vector sequentially, and we are getting that this method is numerically unstable. You have already seen the Professor Hill condition matrix as well. By all case it may not satisfy. There are we will say that this is numerically gram scheme process. We will links the process directly to method. Once a gram scheme process is there, the better method we can give to. So modified gram scheme is a numerically more stated vectors, better handles a near linearly dependency in columns. Say for example, if the columns are not exact, gram scheme process won't give you the result. Say in that case, the modified gram scheme process, it can give you the more stable results. And this produces A equal to QR, this modified matrix, okay. And the difference is that gram scheme process, if you are calculating this QI scheme process, only the initial, only the just previous step requires. But modified gram scheme, all the previous steps it needs to compute the next QIs. Say for example, you want to compute QI, it requires from 1 to I minus 1 this column, this orthonormal vectors to generate QI, okay. But in classical gram scheme process, you just require only minus 1, okay. But in modified gram scheme, he changed that to just from 1 to m, and here you see, so J equal to I plus U, you require to compute the modified gram scheme, okay. 10 to the power minus 10, 1, 0, 10 to the columns of here are nearly dependent, nearly, okay. And the classical gram scheme fails due to loss of scheme maintains the orthogonality. So that means this is a little bit advanced, not instead of gram scheme process, even if the columns of that matrix are not linear. See what exactly we are getting by using the classical gram scheme. This is the classical gram scheme, and this is modified gram scheme. When you compute this orthonormal vectors, that means you will get the orthogonal matrix, and in general you should get Q transpose Q equal to identity, but we are not getting, we are losing in case of the classical gram scheme. Even if these are nearly dependent, you can use the gram scheme process to get the orthonormal vectors, okay. And stability matrices in ill condition problem and stability matters in ill condition problem. Say for example, if you just calculate, you can get this you can get I'll show you in my later slide. Especially important when the vectors are nearly linearly dependent. This is important. Especially important when vectors are nearly linearly dependent. And for over classical gram scheme. Instead of using classical gram scheme process, you can use either if you are calculating the numerical results. So instead of using gram scheme, you just use the Householder transformation. Classical gram scheme process is numerically unstable. Now here we see, and then if you use the classical gram scheme process, you just make U1 equal to B1, and then you are getting Q1 equal to this one, okay. And as you have the R12, and this is Q1 to V2, and you will get this matrix, this is minus 1, these are the scalar, and U2 is a vector, then again you in the second step you are doing this. And if you write all together, you will get this contains this R11, R12 and R22 and 0, okay, or R12, R11, R12, 0, R22, okay, upper triangular matrix, because these are, and this Q1, Q2, it would be in the right and the left hand side V1, V2, V3, okay. In this way you will get V equal to QR, and this is R1, R12, 0, R22, okay, and this V columns are V1, V2 up to V3. So these are, so this from Gram scheme you can write that linearly independent column vectors, and all together you can write in the, is called Vandermonde matrix, like we gave you Hilbert matrix, and it is of same nature. This is also yield condition matrix, okay. So for this yield condition matrix we will check for the classical Gram scheme as well as for the modified identity, that norm should be equal to 0 in general if Q is orthogonal, but classical Gram scheme it fails to give this 0. Say for example, entry is this Vij equal to j divided by 20, and this is I minus 1, okay, and I equal to 1 to 30, and its condition number is 3 into 10 to the power 13, okay. It is a non-square matrix, okay. Instead of indicate columns are nearly linearly independent. These are columns are not exactly linearly independent. It is near. Yeah, if in the linearly independent zone, so it would be nearly linearly. Just to calculate this, and you just choose for the stable method condition number times a unit of 3 into 10 to the power minus 3, if we are accordingly, okay. Now you see, okay, it is not expected, and this for modified Gram scheme it is 3 into 10 to the power minus 4, it is coming in zone 3 into 10 to the power minus 3, so it is a stable, okay, but it follows the condition number times into unit round of error, okay. And similarly Householder transformation or reflectors, as we discussed previously, and this is very good, 1.9 into 10 to the power minus 15, it is gives a very good result, okay. So these two methods, the modified Gram scheme and Householder transformation, even gives better than modified Gram scheme, okay. So QR decomposition results for highly ill condition Vandermonde matrix. So this is Vandermonde matrix, is also this is very ill condition matrix. Also you can try the GNN method by using Vandermonde matrix. So this is another tutorial for him to check for the Vandermonde matrix to get whether GNN is stable or not. Okay. The fails in preserving the orthogonality for ill condition matrices and more stable but still sensitive to ill conditioning, and sensitive to ill conditioning because this is near to unit round of error. You see 3 into 10 to the power, but for the Householder highly stable, because you see the result you got in our last slide, it is about 10 to the power minus 15, but in case of Gram scheme is 10 to the power minus 4. So that's why we have written, but still sensitive to ill conditioning, near to, okay, and this is highly stable. So that's why I told you before that QR decomposition by using reflectors and rotators is highly stable. So you can use this method when you do the numerical calculation instead of using LU decomposition, okay. Now next we will discuss about the singular value decomposition. This is very powerful and everybody use, and yeah, Moore-Penrose inverse you are using also in the GNN, and we will read little basics, and then we will see the what is the Moore-Penrose inverse, how it connects with the usual inverse of matrix, if how it's what's the relation, and so what is the relation between the eigenvalues and the singular value decomposition, okay. In general, eigenvalues you are calculating for a square matrix, and for singular value decomposition you can find for the non-square matrix as well, and for singular matrix as well you can find, and later on you will see the singular value decomposition would be much more powerful, means you can get eigenvalue decomposition from singular value decompositions. So if you don't know eigenvalue decomposition, you know singular value decomposition, so you can work out all these eigenvalue things. Okay. Okay. So here the singular decomposition is a highlight of linear algebra. This is any m by n matrix, square or rectangular, and its rank is R. We will diagonalize this A, but not by x inverse Ax. In general, this if A is a square matrix, and then we write x inverse Ax something. Okay. And the eigenvectors in X have three big problems. What that big problems? They are usually not orthogonal. Okay, they are not usually orthogonal, because you see, if it is a Hermitian matrix, then you make a diagonalization, their columns are orthogonal. But if it is on the other matrices, it may not be, the columns may not be orthogonal, is not it? So similar matrix, a matrix is diagonalizable if it is similar to diagonal matrix. Okay. But their corresponding this columns of this X may not be orthonormal or orthogonal. Why, instead of some special matrix like Hermitian, normal, all such kind of matrices, and their columns, matrix columns, matrix means that X inverse this, its column, X column, all are orthonormal. And here they are not always enough eigenvector, and Ax equal to lambda x requires A to be the square matrix. When A is a square matrix, then you can find the eigenvalues. So this is one demerit, and singular vectors of A solve all those problems in a perfect way. Singular values, and also there are many applications to this. What is this? Suppose a matrix is a non-square matrix, R n cross n, be a non-zero matrix of rank R, then you can write this as VD. There exist orthogonal matrices, and U is R n cross n. This is square matrix, and V is M by M matrix, and this U and V are orthogonal. Okay, and a diagonal matrix sigma, it is not because in general we used to tell if it is a square matrix and we are telling diagonal matrix, and this looks like a diagonal matrix because its diagonals are non-zero, positive, and the rest of the entries are 0. Okay. Now here you see this, these are called if U1, U2, Un with this property, because orthogonality condition is satisfying, and the V1, V2, Vm because its size is n by n and this size is m by m, and V transpose V equal to I am evaluating. If the rank of the matrix is R, then you can write sigma 1, sigma 2, sigma r. That would be 0. Rest of the entry, this should be dotted 0, and this should be like the size of the matrix what we have. And this is strictly this one is all non-zero positive. So all these positive are the singular values of the matrix. Okay, these are called singular values of the matrix. Okay, and the decomposition is a form. Any real matrix you can have this one. Okay, and then you have what is the maps the orthonormal basis vectors of Rm to the scale orthogonal vectors in Rn, that is equal to each sigma I represent the stretching vectors along with the direction Vi, and the rank R of A equals the number of non-zero singular values, because in case of Ax equal to lambda x, it scale in the same direction, but in singular values it won't scale in the same direction, in different direction. It forms the ellipse. Okay, because different. A Vi equal to sigma I Ui. The left hand side vector and right hand side vector are different. Okay, but in eigenvalues they are same. Ax equal to lambda x. Okay, and it will scale in the same direction, but it will move in the different direction. U and V are orthogonal, and sigma is diagonal with the diagonal, and this SVD is a fundamental tool in numerical linear algebra, data compression and the PCA. Everybody is using the singular value decomposition. This is again a stable decomposition, very stable decomposition. The Moore-Penrose inverse, whatever people are using, are coming from this singular value decomposition. You can derive all these Moore-Penrose inverse from singular value decomposition. That's why people are using, because in Moore-Penrose inverse you have 4 inverse, 1, 2, 3, 4. And if you are using 1, 2, 1, 2, 1, 2, 3, like all these generalized inverse things would be outer inverse, generalized inverse, and all such things would be coming. Okay. If you do write that equation, that is A equal to U sigma V transpose, and if you do write, you will get A V I equal to sigma I U I, because these are the contents V1 to Vm, and this is Rm, and you just write this is U1, U2 up to Un, this is Rn, and this, if you do write, you will get this A V I equal to sigma I U I varies from 1 to R, and this would be 0 for I equal to R plus 1 to N. And this Bi is equal to right singular value, because it is in the right, and this is called left singular vectors. This is Bi is the right singular vectors, and this you can tell left singular vectors for corresponding to singular value sigma I. Say for example, you are telling the eigenvectors lambda I corresponding to eigenvalue lambda I corresponding to eigenvectors Vi, say, or xi. So likewise here for this singular value, each of the singular values, it has right singular vectors and the left singular vectors. Similarly, if you do its transpose, and you will get At Ui equal to I varies from 1 to R, and this is N, R plus 1 to N. Okay. It maps the unit vectors V to the scaled orthogonal vectors sigma Ui as A V I equal to sigma I Ui. The first R directions are scaled by sigma I greater than 0, and the rest are mapped to 0. Just we have the image of the unit sphere under A is hyper ellipse, as I told you that it makes a ellipse. Now you see, if you have this and you got this sigma I, and then A V I equal to, you just multiply here V I, and then you will get sigma I U I, because here V I, if you take V I transpose and V I, this would be 1, and the rest of the entry would be 0, because like vectors would be 1, and unlike it would be 0, because they are orthonormal. Okay. So finally you will be getting only the one entry, that would be sigma I, and the rest of entry multiplying it would be 0, because you are multiplying with the Vi vector. Okay. So only I. And the matrix multiplication A B equal to U sigma implies that each Vi is mapped to sigma I Ui when sigma I equal to 0, and you will get A B I equal to 0. Okay. Thus the geometric form follows directly from the standard singular value decomposition expression. Now we are getting the 4 fundamental subspaces. That four fundamental subspaces are of this this fundamental subspaces, this range space, and that is equal to column space, and which equal to span of U1, U2 up to UR, which is in Rn, and null space, that is null space of this one Vr plus 1 to Vm. You have already seen the first part you are getting sigma Ui, and the rest part from R plus 1 to M, it is 0. And similarly in the transpose part, you are getting from 1 to R, you are getting At Ui equal to sigma I Vi, and this will be in Rm, and the null space it is in the R plus 1. So it generates the 4 fundamental subspaces generally, and this follow directly from this SVD, as we have seen from the beginning here. Here we are getting all these 4 fundamental subspaces. Okay, and this is in the range space, and this is null space, and it's a transpose. This is a range space, and this is in the null space. Okay. So here is one corollary. This range space from the dimension of null space, it would be M. There, that is The sum of the dimension of the column space and the null space equals the number of columns. Okay. And this result also known as the rank nullity theorem. So, you are this result you are getting from rank nullity theorem from the linear algebra. Okay. The follows from the orthogonality and the completeness of the and similarly we are getting dimension of range space of AT and dimension null space of AT equal to n. So, here is M and this is L, because this matrix is non-square matrix. In our square case you would be getting one result, and here you are getting the two. Okay. Okay. Clear? Now you see. So, here we can write this as a sigma 1, the rank 1 matrix. Generally in the rank 1 matrix what you are doing, so A equal to U sigma Vt, okay, this you have, okay, and what you are doing basically, if you write this A matrix, you can write this is summation of, okay, sigma I Ui Vi transpose, I varies from 1 to R, yes or no? Because its a dimension, this rank is R, so only it has the R diagonal entries. So, if R diagonal entries are there, so only sigma 1 up to sigma R, and the rest of this would be 0, and this is U1, U2 up to Un is there. Yes, it is Un, and this is V1 transpose, V2 transpose, and this is coming M transpose. Yes or no? So, what we are doing, since all the entries are 0, so there is no impact after UR and there is no impact after VR, all would be coming to 0. That my point. Because these are 0, after this all are 0. So, you are multiplying again and again with 0. So, finally, you would be getting this, because just you multiply U1 sigma 1 V1 transpose, U2 sigma 2 V2 transpose. Likewise, you can write this matrix. Okay. So, this is first one is this rank 1 matrix, this is U1 and V1 transpose. So, you are just adding the sigma 1 U1 if it is a rank 1 matrix. So, if you want to generate a rank 1 matrix, simply you just compute the singular value decomposition and get the rank 1. If you want to get the rank 2 matrix, you just add sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. So, rank 2 matrix you can get. So, rank 3, rank 4, rank 5, rank R, how much rank matrix you want to generate, you can generate from singular value decomposition. Okay. So, here is the proof. If you want to prove the singular value decomposition, here is the simple proof. Let we can go through induction. Say the theorem is true for n equal to 1. So, rank 1 case you just think the columns and you just get the sigma singular value decomposition. How you get this? All the columns lie in the range of A equal to span of U1, and choose this U1, this norm equal to 1, and then A equal to U1 V transpose for some W in Rn, and define the V1. You just choose the V1 in like this, and sigma 1 just you take the norm of this, then you can create this rank 1 matrix. Oh, this is true for rank 1. So, similarly, you just take this is U1 is orthogonal on orthonormal basis, and you just choose this U, and V1 to V you just write this one, and define this sigma likewise for the 1 case, rank 1 case, except sigma 1 rest of the 0, because if you want to create for the 2, so you have to keep sigma 2 here. For sigma 1, so you get A equal to U sigma Vt, where A is a rank 1 matrix. Why rank 1 matrix? This is sigma contains only one non-zero singular values. Okay. So, for this whatever you will get this rank 1 matrix, you will get this gives SVD of rank 1 matrix. Understood? Okay. So, similarly, you just say for example, this is true for the rank R, okay, and then we can prove it is true for r plus 1, say. Okay. And V1 this maximize, and just you define the U1 with this, and define the sigma 1. This is you know that sigma 1 already we have discussed. This is 2 norm of matrix, and this sigma 1 is the maximum singular value of the matrix A, and here is sigma 1, and all will follow. Sigma 1 is greater than equal to sigma 2, greater than equal to, and so on, sigma r, which is strictly greater than 0. Okay. So then you will get this one, and now you define this matrix B equal to U transpose A V sigma 1 Z T and A 1. So if you can make this equal to 0, then what you have, the sigma 1 already you got, and this is say say this is rank say r or r plus 1, whatever it is. If B is the size of the matrix, say it is r plus 1, and this is sigma 1, and this is A 1 is of size r, and by induction this has a singular value decomposition. So you can write this unless you z equal to 0. So first you have to make z equal to 0 and u equal to sigma Vt. Okay. So if you suppose B equal to this one, and just take this vector x equal to cos theta sin theta w, w equal to 1. If you take the norm of this, you will get this one. Since sigma 1 is the largest singular value, for the optimization it implies the z equal to 0. So obviously z equal to 0, from here it is coming. Once you put z equal to 0, then you have this sigma 1 0 0, B you got this one, and the rank of A1 equal to r minus 1, say. Because we are trying to prove this one more rank, and since sigma 1 is there, and the rank, because the theorem was true for rank 1 minus 1, say r minus 1, say. So you want to prove for the rank r, say, and for 1 it is true. Assume that this is true for r minus 1, and then you can prove for r. So this rank A1 is r minus 1, and then by induction you can write this A1 equal to sigma 1 U1 sigma 1 B1, and this is the size r minus 1 by r minus 1, and this contains all these diagonal entries are singular values, okay, non-zeros. So once you do write U1 equal to sigma 1 U1 V1, and then you will get the entirely U sigma 1 0 sigma 1 V transpose. So likewise you can prove the singular value decomposition by induction. Okay. This gives singular value decomposition for general A matrix of rank R. So now you can get the condensed form of SVD, as we have seen for the QR decomposition, condensed form. That means unnecessary 0 you want to remove. Okay. Say for example, here we have removed this. Say all the zeros are there. If you 0, you will get this I varies from 1 to r, and this is nothing but UR. This is UR sigma transpose sigma VR transpose. This is R. Okay, and this matrix you can write sigma. This is okay sigma R, and this is 0. This is correct, because the connected this all this this left singular vectors and the right singular vectors will be 0. So you will get the condensed form of this. This is of size this is n cross r, left hand side this is n cross r, and what would be the size of this? Sigma is r cross r, and this is m cross r, and left hand side is n cross m. So it is well defined. Okay. So if A is a very big matrix, say, and it has a lot of non-zero entries, and the right hand side you have the very compact form, and where U, R, and B are orthogonal matrix, and it contains diagonal contains only R non-zero singular values. Likewise, you can compress your data. So you have lots of data in the left hand side. You are compressing the data with the help of orthogonal matrices. So here is the size n by m, and this sigma r contains only r by r, and it is connected with the r non-zero singular values. If you want to compress again further, so what you do, you just from the last side you just remove that, you just remove some of these singular values which are near to 0, and in that way you can again compress your data with the beautiful way. Okay. And the proof is as usual, just as I did here, and this is the way you are doing, and finally you are removing the 0 blocks. You are removing 0 blocks. Okay. Now you want to compute this, the singular values. How you will complete? You just take the A transpose A, and this you have this, and find the eigenvalues of this. And once you find the eigenvalue, and you take the square root. So all these would be the singular values of that matrix. Okay, and it would be non-zero because this A transpose this matrix, you can find this is a positive definite matrix, and all these eigenvalues would be positive. So you just take the positive square root. Okay. So here you got the sigma 1 and sigma 2, and then you have the singular vectors, corresponding singular vectors. So you just a v I equal to sigma I u I, and like you are solving a x I equal to lambda I x I, here a v I equal to sigma I v I, then you can find, because here is I think this eigenvalues, eigenvectors we are finding, because once you got the singular values, these are sigma 1 square, in this is sigma 1 equal to this one, and this eigenvectors of this, because eigenvalues are, what would be the eigenvalues are this one, Anna? 45. No, this eigenvalues 45. Yes, eigenvalues are, and the singular values are this one. Okay, just square, and this eigenvectors you can find with corresponding the eigenvalues 45, and you got this eigenvectors. And sigma 2 square, you also got the eigenvectors from here V2. Okay, V1 V2 you got. Once you got V1 V2, and this A V1 equal to, you have this sigma 1 U1, you see. Okay, and this V1 and whatever vectors you have this for root 45, because this is the singular value, and the rest of this are U1. So likewise, from the eigenvectors you can get the singular vectors. Okay, you got the eigenvalues, from eigenvalues you got singular vectors, and from singular vectors and the eigenvectors you got this U1. Okay, so this is nicely connected with the eigenvalues. And similarly A V2, this is A, and this is V2. Okay, just V2 as we calculated this V2, say, and this you calculated, and then this is the root 5, and the rest of this is U2. So then once you got this U1 and U2 and V1 V2 already you have, you have calculated, and you got U1 U2 you got, and then also you got the singular values, and then you got this sigma, that is the singular value A V equal to U sigma, and U transpose A V equal to sigma. So if you have the matrix, a non-square matrix, you just take A transpose A or A transpose, but eigenvalue would be remain same, but you have to see that condensed form you can get this. Okay. Okay. Next you see that how this A is the sum of the rank 1 matrices. These are the sum of rank 1 matrix. You see this is sigma 1 U1 V1 transpose, and sigma 2 U2 V2 transpose, and then you have this just you add this, and this is rank 1 matrix, and this is rank 1 matrix also. You just put this and you will get this here. Okay. Now you consider another example. This is for the condensed form, how you are getting, and if you remove the zeros, you won't get loss anything. That means, okay, as I told you here, sigma r u r sigma r v r, you can remove 0, and here also same thing, we can remove 0. Here all eigenvalues of A are 0, and only one eigenvector, this is 1 0, but singular values are sigma equal to 3 2 1 0. But singular vectors are column of the identity matrix. This example shows how the SVD provides much more structural insight than the eigen decomposition, especially for the non-symmetric or defective matrix. Okay, non-symmetric and defective. This would give you more structural insight than the eigen decomposition. How you will see this? Now say HBD setup, say A equal to U sigma V transpose, and then you have this one, and then you can find the least square. How you are finding the least square solution? You just check that suppose you need to find the x for which this norm is minimum. So you just apply U sigma V transpose, and then you can get your solution. You have this A equal to U sigma V transpose. Now you need to find the minimum of x, and this is Ax minus B, and this is two norm you are taking. This you just U sigma V transpose, and this is x minus B, this is norm 2. Okay. Yes. Now I will take this you just sigma minus, what you will take this, or if your U transpose B, and what do you make this one? BV, and can I take this norm 2 and into say whole into you are taking common, and here you are taking VT common, VT, okay, VT, this, yes. So I will get this U is U, these are orthogonal matrix, and this is invariant under 2 norm, okay. This norm is 1, so I will get simply U transpose BV, yes, yes or no, this I will get, okay. So this is what we got this. Huh? I x we move this one. Yes. U sigma V, this x is that, this x is that. Huh? Summation. Ah, okay. V transpose x. Yes. Yes. So you have sigma V transpose x. Okay. So if you have V transpose x, but here we should get something. Okay, yeah, let's see here. Okay. So what you are doing is that, so anyway, you are doing this, you are taking this, you take common first, this is identity, this VTX, and this is U taken, and this is U transpose, okay, and this is V, this is correct. And then again one more step we will be doing, this is norm U, this would be sigma, again V transpose you are taking out, you cannot take out because this V transpose is there, okay. So what you do is that, so what we will do? Okay, yes, yes. You take this is U, this is sigma y minus UTB, and this you have taken, this is C, okay. This is norm sigma y minus C, this is norm 2, this is what we have done, okay. Okay, so one you have got sigma y minus C norm 2 square, this is vector norm, and then you take this sum of this square and the remaining, because you know C has n elements and this has a lot of zeros also, okay. So it has R non-zero C sigma I U I minus C I, and the remaining I varies from R plus 1 to n C I square will be there, okay. And this is dependent on y I, but this is independent, okay. So this would be minimum when this would be equal to 0. So we have made this equal to 0 when this is equal to. So because if you make this equal to 0, then you will get this. You know? The minimum will happen when this part would be equal to 0. So you have, for equating this equal to 0, you are getting yi equal to ci sigma I. This yr plus 1 and yam arbitrary, as we have seen from the QR factorization, that if it is a over determined system and its rank is r is less than minimum of mn. Okay. So in that case we got infinitely many solution, and similarly here we are getting for why I varies from 1 to r, because r is the rank of this sigma matrix, okay, sigma r. So up to this we have the unique yi, and the beyond this yr plus 1 to ym you have the arbitrary. Okay. So likewise you will be getting the infinitely many solution, but the least square solution means you will find the one which gives norm minimum. Okay. So here we are finding the to find the solution x with minimum this, we must minimize this one. Okay. We are just because this is achieved when this equal to 0. So you can make all this, because these are arbitrary, let it the one choice all 0. So you will get this solution, and that solution is x equal to vy, and this all this sigma I, because yi you got the sigma I because v varies from 1 to r, the remaining terms is 0, and this sigma ci by sigma I, because yi equal to ci by sigma I. Okay. Because this if you multiply, then you will get this one, and this is nothing but again Moore-Penrose inverse. We have seen in the QR factorization Moore-Penrose inverse. This is, I will discuss what is the Moore-Penrose inverse of this. The Moore-Penrose inverse is generally we are writing this one. You have this general inverse, you have a equal to this and a plus, because we are writing a plus instead of a minus, because we are not finding exactly the inverse of a matrix, and here we are compromising something, because our matrix is non-square. Okay. So what we have, this what is the size of this matrix? N cross n, n cross n, this is m cross m, and this is n cross n. Yes. So what we are doing, we are doing sigma v transpose. This is plus. Okay. If it is a square matrix, we will make it inverse. If it is a non-square, we keep it as plus. Okay. So what we are doing, the v transpose, this is inverse, and this is sigma plus, and this u inverse. Okay. This is the way, this is the technique, because this is inverse, this is not square matrix, this is square matrix. So we are taking usual inverse, and this one we are taking plus, because, and the v transpose inverse is what is v, and this sigma plus u inverse u transpose. Okay. But sigma is nothing but, if the rank is r, we have sigma r, and this is 0. Yes or no? Yes. And again the sigma r is a square matrix. What we are doing, this sigma plus is just we are writing the only the square part, we are keeping this sigma r inverse, and the rest would be as it is. We are not changing anything. In general, we should take 1 by 0, no. But here is the, we are compromising something. We are not doing the exact arithmetic here, and we are putting here 0 as it is. Okay. And here sigma r inverse. So here sigma r inverse. So sigma plus, that means this is sigma inverse. This is 0 0, and this matrix you will be getting this is 1 by sigma 1, and then 1 by sigma r, and the rest would be as it is. Understood? Yeah. So this is the way a plus we are defining sigma v, sigma plus, this is v sigma plus, and u transpose is the Moore-Penrose inverse, and it is called sometimes pseudo inverse. Okay. And this is the one we have, this is a plus, you got v sigma plus u transpose. Okay. U transpose you got, and where sigma plus is 1 by sigma 1 and up to sigma r. Okay? Any doubt? Okay. And now this representation is exact and satisfy all the 4 Moore-Penrose conditions. The 4 Moore-Penrose conditions I can, and also same thing in case of condensed form of singular value decomposition. If you have, then you are just taking A plus equal to this one. You already know that A plus we have A plus equal to, already you got this U R sigma and the V R transpose. Yes or no? This is sigma R. R is it? Is it? Yes. U R sigma R, because sigma R is R cross R matrix. But here you are getting same thing. This V sigma R inverse. Okay, and the U R transpose. This is A plus. This. If you write in the condensed form, so as usual inverse you can take this left hand side, this one, because again the sigma R inverse means because VR is UR transpose and the VR is that. So you can get this. This matrix is efficient and commonly used in numerical computations. So condensed form people are using instead of taking all the zeros, columns, zeros involving with the columns of the matrix. So if you do solve this minimum of x with the singular value decomposition, then you will get the solution x equal to A plus B, and this is called the least square solution. Okay. So if you know the Moore-Penrose inverse of a matrix, and then you just put that A plus, you will get the least square solution instead of calculating all such things. Okay. The works even when A is not full length. As we have seen, R is a rank of a matrix which is not the full length, and for the full length also it will work finely. Same way, provides the minimum norm solution when they are infinitely many. If you have infinitely many solutions, you can find the one which gives the minimum norm. So that x would be the least square solution. The pseudo inverse is essential in data fitting, control theory, and the machine learning. So many people are using, as I told in my first class, this is the optimization where you have the constant is one constant you have. If you have many constants, minimizing, then in that case what you are using? You are just taking the help of machine learning people are doing by using Lagrange multipliers. You just take all the Lagrangian and then you find the critical points. Then you take the help of operation research and a primal and dual. And so then finally you are getting the optimization, optimal solution. Okay. Sometimes you have seen lot of constant would be there. So minimization over this, over this, over this, and control equation you will see there are many constants would be there. So when you do LPP problem, you have lot of constants. Minimum over this condition, this condition, this condition. Is not it? In that situation, you have to take the help of Lagrangian multiple, and then you have to find gradient method to solve that equation. Okay. So during that time also you use the singular value decompositions for. Okay. This is one. If all these 4 conditions will be satisfying, this is called Moore-Penrose inverse. Already professor is discussing about the generalized inverse. And from here, all this, if you one drops, then again inverse, some people are working, lot of works, research work is going on. And 1 inverse, 2 inverse, and 3 and 4. If all this 1, 2, 3, 4 would be satisfying, that is called Moore-Penrose inverse. And this is very, very stable, and this gives you very right result. Okay. And if you one drop, then you will get 1, 2, sometimes you will get outer inverse, and sometimes you will get generalized inverse, 1, 2 inverse, 1, 2, 3, 1, 2, 4, so 2, 3, 2, 4, like this. So as per the application, there are a lot of things, and this is exactly same things for the non-singular matrix. If you have this, all these 4 conditions will merge into 2, is not? If A is a non-singular matrix, by the definition, if A is non-singular, by the definition there exists B such that AB equal to BA equal to identity. Okay. This is one you know that if A is a non-singular matrix. So here, if A is a non-singular, suppose B equal to A inverse, you just put it, you will get AB equal to BA equal to identity. Understood, man? You just put A equal to B inverse. Then you will get this. Again A equal to B inverse. You will be getting this. And A inverse, you will get AB equal to identity and BA equal to identity. So all these four conditions will be merging into this one. So the pseudo inverse is the generalization of the usual inverse. When A is a non-singular matrix, then all this pseudo inverse merge into one inverse. This if B equal to A inverse, from SBD all four properties hold. Conversely, any matrix B satisfies these four conditions must be A plus. So whatever we have given the singular value decomposition, all these four conditions would be satisfying. What we gave this A plus equal to this is B sigma plus U transpose. This condition you just check all this pseudo inverse condition, all four conditions would be satisfied. If this is your A plus, and this is pseudo inverse of A, and say this is a B matrix, okay, then all this A equal to A, and B equal to B, and you have AB transpose equal to AB, and this BA transpose equal to BA. So what do you substitute? Just in place of B, you just put this one. Okay. And all these four conditions is satisfying. So pseudo inverse, whatever we are getting from singular value decompositions, we have time is there. So pseudo inverse, whatever we have this, you will get A B A equal to this A B equal to B, and AB transpose equal to AB, BA transpose equal to BA. So all this satisfy. Conversely, any matrix B satisfying these four conditions, you can get this must be A plus. Okay. So similarly, you have this other form also. This A is n by n if with the full column rank, full row rank, and the full column rank is also there. So just you are writing the sigma in this form, diagonal of sigma 1. This is a big rectangular this side, rectangular this side, and rectangular this side. So that is the way you have this n cross m matrix, and A equal to sigma B transpose. Okay. Now here you see this matrix A transpose A. If you do right, you will get the sigma I square, as I told you. The sigma I square means this ith singular value, and this if you ith inverse, if you find this AT inverse, this is nothing but, and if you do calculate, because V are orthogonal matrix, and this would be 1, and then you will get 1 by sigma I square. Okay, that means yes, you will get the diagonals are 1 by sigma I square, sigma 1, sigma 2 up to sigma r. Okay, this only ith term I have written. This is nothing but the sigma matrix contains sigma 1 square, sigma 2 square till sigma r square. Okay, so because here you see A transpose, this is U sigma V transpose, and this is U sigma V transpose whole transpose, is not it? And this is your U sigma V transpose, and this is V sigma U transpose, and this is your identity U sigma sigma, this is sigma square, because this is a real matrix, okay, and this is V transpose. Yes or no? Now you have this U, these are the sigma 1 square, and this is sigma r square, and this is 0, 0, and this is V transpose. Okay. So now you have this A transpose, A transpose. If you write this, okay, A transpose, yeah, okay. You write this is V transpose. This is equal to U sigma 1 square, and this is sigma r square. This is 0, and this A transpose, yes, this is V. Okay, this is V, and this is U, this sigma I square 1 square, and this is sigma r square. This is, and you would be getting A transpose V I equal to sigma I square U I. Okay, this we need to these are the singular values of this. Okay, I V I equal to this one. I varies from 1 to r. Similarly, you can get 1 by sigma I square. Yes, and then if you do calculate, you will get 1 by sigma I. Again, you just do this. What we have got this. These are symmetric and positive definites, because A transpose A is symmetric and positive definite, and this, if you do calculate with this operating A transpose, this is pseudo inverse. What the professor is using this notation always, you must be seeing that this notation. Instead of this, he is using this Moore-Penrose inverse pseudo inverse, and for the reverse, this would be the pseudo inverse, that is the Moore-Penrose inverse. So Moore-Penrose inverse, sometimes it is called a pseudo inverse. Okay. All SBD use the same orthogonal matrices U and V, but scale differently. Now you can think about that eigenvector, singular vectors may be infinitely many. Singular values are fixed. Why? This U and V, they are scale dependent, because if you have a unitary matrix or orthogonal matrix, like you are putting AVI equal to lambda I VI, if you VI you scale it, again that would be the eigenvector corresponding to same eigenvalue, is not it? And similarly here, the single, if you do scale both sides, and the singular value will remain unchanged, and the singular vectors may change. Okay, so that's why the singular vectors may be anything, because for this U and V can be different with same singular values. Okay, that you have to be. Now here you see, suppose you have this. Now you will drop this some rows and the columns, as I told you. If you have the earlier we have taken A matrix, and if you do transpose this, and you will get this, both this, you can see both the matrices have same singular values. Either you left hand side or right hand side you take the transpose, and the eigenvalues of this are this one, sigma square equal to 941, and the corresponding singular values you just do the square root of it. Okay, or you will get this. Now what my intention is to show you that you can write in the rank 1 matrices, some of the rank 1 matrices, like you got the, once you got the singular values, and you know how to find the singular vectors. So once you got the singular vectors, you write in the column wise. Okay, and these are the your this one, and these are the singular values, because you have only 3 singular values, and the one is 0. Okay. The first column U1 and V1 have 1s in the position 3 and 4, and then the matrix sigma 1 U1 V1 picks out the largest number in A, which is A34 equal to 3. So with this corresponding to, you can write this as a 3 U1, because 3 is the singular value, and 2 is the singular value, and 1 is the singular value, and this is U1, U2, U3, U4, this is V1, V2, V3, V4. Okay, and if you do write this, and you will get the matrix A, original matrix A you will get. So that means this matrix, if it is a 3 rank 3, then you have rank 1, rank 2, rank 3 matrix you can write. Okay. Now you see here the condensed form, suppose you are removing a 0 rows. The 0 rows, as I have shown you, that if you have lot of 0, if the rank of the matrix is say 3, size of the matrix is 4, rank is 3, so we don't require another row. Okay, we can remove that one. So likewise here we suppose we remove the last row A, and then A becomes a 3 by 4 matrix. As a instead of 4 by 4, it is like 3 by 4 matrix, as we have seen from here. Okay, a matrix AAT becomes 3 by 3. If you do AAT, if you write, then you will get 3 by 3. It's a fourth row, and the columns disappear. Okay, and however the eigenvalues of ATA and AAT remains the same. It would be remain same, that is lambda equal to 1, 4, 9. So the singular values would always, I told you that the eigenvalue will remain same. If eigenvalue will remain same, then singular value will remain same. That singular values are as it is, because this is 1 plus, just you take the square root of it. You have 3 to 4. We just remove the last row of sigma and the last row and column of u. So because once you are removing means there is no point to keep the columns corresponding u and v. So we have removed. So now it looks like a 3 by 4, u 3 3, v 4 4, and this is sigma 3. The SBT naturally accommodates a rectangular matrix. So rectangular matrices you can write with this notation. Now we can discuss. And time is there? How much?
Time to finish.
Finished?
15 minutes.
I ask you. Okay. So next class we discuss about that stability and other things, and with this I'll stop here. Thank you so much. If you have any question, please.
Sir, finding eigenvalue is itself very hard and computationally expensive.
Yes,
thing.
next class I will be discussing on this, because how it is difficult and how stable way we can compute the eigenvalues. Okay. So next one more class is there. Maybe if I get more class, I can discuss how stable way we can compute this eigenvalue. That is called a QR algorithm.
So for finding singular value, does there any exist direct method to find the singular values directly, or we just update the existing numerical methods of finding eigenvalues and take the square root?
If you know finding the eigenvalues, then you can find the singular values as well, because they are well connected and they are vice versa. If you one you know, other you can know. Because at the end you would be getting a matrix. A is a matrix, you are finding eigenvalue. ATA is a matrix, you are finding the eigenvalue, and you are just taking the square root. So once you know how to find the stable way of getting this eigenvalue, then I think it will work. So next class I will discuss about how stable way to calculate the eigenvalues. Yes, non-zero positive, non-zero positive. Yeah, give the mic. You take, because it is live. Give to him. You know. So if no questions, we will stop here. Yeah, the mic.
Present 2 comments.
Mic. Because I have given you one this Bender-Munde matrix.
Only 2 comments as addition to
Yeah,
your
please.
interesting lecture. In page 62, I think it was here is it was condensed SVD.
Yes.
Condensed SVD.
Yes.
In condensed SVD, A dagger includes inverse of sigma
yeah.
r.
Yes,
This-
because this now, but this now rectangular matrix. This is rectangular.
No problem.
This is rectangular, but this is square matrix.
Yes, but this sigma r minus 1 is defined using 1 by
Yeah.
sigma 1,
Yeah, yeah,
which is typically not problem.
not problem.
Then 1 by sigma 2, which is bigger problem. And finally 1 by sigma r, which can be very small.
Yeah, yeah, yes, I agree,
And
I agree.
sigma r can
Yes.
be very small.
Yeah,
And,
computation singular values is
and
also.
then 1 by sigma
Yeah,
r is
yeah.
catastrophic
Agree.
for numerical.
That's the question, how stable way we can calculate this.
Yes. So it is better to skip such small
Yes, exactly.
singular values.
Yeah, because those are very near to zero. Say the data compressing and this image processing
Yes,
people,
it
what they
leads
do,
to data
if
compression.
this sigmas are very near to zero, because if you make the reciprocal, it would be problem. Is not it? It would be problem. What they do, they remove these zeros, which will make difficulties. That's my point.
Remove such
So
singular
once
values.
you remove those difficulties, then again your data will be getting compressing again. You know? Beautifully you are getting. Say instead I require, say my sigmas are very near to zero except 5 singular values. 5 singular values I can calculate very good way. Otherwise there would be stability problem. So what they do, they don't take the challenge. They keep that 5 singular value, and all this calculation they do with these five singular values. Yes.
Yes.
Because they remove all this. But
put
as this
zero
is
and-
theoretical, I am just teaching you linear algebra. I am not talking now numerical linear algebra. Okay, when you compute this, again that is a challenge. Sigma r is there. If they are very near to zero, then it won't give you. So that's why. So data compression, because they are engineers, they don't know all this very fine way. So they remove this, only the bigger terms they keep. That's why they keep the first one is maximum, then second, then third. So likewise, just they run this, cut this, keep this. So accordingly, if sigma r, if I am putting 5 by 5, they will take 5. Okay. So the left hand side size of the matrix and this size will remain unchanged, will never change, because this is n by r, this is m by r, है this is n by 5, 5 by m, and this is 5 by 5. Then calculates. Okay. So don't go for the danger mode, and that is enough.
It is so-called truncated
Yeah,
SVD.
yes.
Truncated.
Yes.
In image restoration is such application.
Yes. There are
Data compression.
data compression.
Low rank approximations.
Low rank approximations. Because here you can find the rank of the matrix. If just dropping this, that if you are 5 by 5, you are taking, the rank of the matrix is 5. Left hand side would be 5. Okay. If you are taking R is a 100, the rank of this matrix would be 100. So it depends on the singular values. If non-zero singular values you have, that much rank is there.
In one paper, reviewers asked how did you compute rank of matrix? We can compute rank of matrix different values. One of value, different methods. One of methods is SVD.
Yeah, one.
And numerically rank of matrix is not the same.
So my next slide was like this. See, my next slide was the problem metric. You see, I have given here eigenvalue stability singular values versus eigenvalue stability here. I have given where is the problem. You see the small change in the fourth one entry, 1 by 60 creates a much larger effect in the eigenvalues of here. Originally with a 0 in the 4 1 position, the eigenvalues of A are all zeros. Okay, all amla 0 0. And after the change, the eigenvalue moved to 4 points on a circle in the complex plane center at the origin with the radius 1 by 10. You will be getting the sigmas like this, and here the great change. You see how this near to 0. So what they do is they remove this part, danger part. That my point. They remove this, only they keep sigma equal to 3 to 1, and a singular value essentially unchanged. The fourth piece of the SBD is like this, one single. The mostly 0 except for the new small entry. That my point.
Mhm.
So there are instability is there of this. Okay.
And only one comment more.
Ah.
SVD can be used not only in computation of Moore-Penrose inverse.
Yes.
For example, it can be used in a computation on one inverses, inner inverses.
Yes, yes.
Only
yes.
3 0 blocks can be arbitrary.
Yes, yes, yes.
And if we change equations, matrix equations, we
Yeah.
will obtain different classes. So
Yeah, we can use
inverses.
for the one inverse and outer inverse also.
Yes, and all will be changed.
So there is a book,
three
this
blocks.
book is there, this Israel something. I think they have used this singular values concept to give the result on generalized inverse. That may be. Yes. One, you have seen, na? That is, you have used this one, and the one inverse, how to consider one inverse, 1 2 inverse, and 1 2 3. This, yeah, correct. This is very, very interesting.
Three blocks change.
3 blocks. Yeah. Yeah.
Sigma minus 1 stay.
Yes, yes.
Thank you.
Okay, thank you so much. We'll stop here. Okay. So today morning we discuss about some ill conditioning problem about the classical Gram-Schmidt and modified Gram-Schmidt and the reflectors. And so basically what is happening during your research time, you have to find a problem which is a little bit difficult. Otherwise, easy problem everybody is tackling. Got my point? Sometimes it will happen, whatever you are doing, maybe some other people might have done within this tenure. Is not it? It is happening like this. Okay? So sometimes you will take the difficult challenge problem. Otherwise, once you will get something, then you will feel relaxed. And whatever you will be doing, that would be safe. for you. Now otherwise, say for example, some ill condition problem, some algorithm fails that you have seen, okay, like Hilbert matrix and big conditioning and a lot of things are there. Now the question is, in application point of view, whatever this Hadamard matrix, Wilkinson's matrix, they are very, very useful in quantum computing. Okay, people use Hadamard matrix, Hadamard product, quantum computing they are using. That is the best way of. And some matrices like Wilkinson's, there is a book called Algebraic Eigenvalue Problem by J.H. Wilkinson. It is this much book. So finding eigenvalues also very challenging. Computing eigenvalues are challenging, is not it? How to compute the eigenvalue? You know the power method. Power method, you find the largest eigenvalue and its corresponding eigenvectors. Okay, that is for one eigenvalue you are finding. But how you will get all the eigenvalues at a time? If a matrix n by n matrix, so you will find all the eigenvalues. And once you got the eigenvalue, whether these eigenvalues are well separated to each other. Otherwise, you know, one eigenvalue, if they will meet another eigenvalue, then all the properties will change, is not it? Say eigenvalues are simple. A matrix is there, eigenvalues are simple. I will do little change. Then that property will be missing, is not it? The simple eigenvalue, it may be the defective eigenvalue. Okay, simple eigenvalue, if you have matrix, then it is diagonalizable, then things would be easier. And if it is defective, it doesn't have enough this eigenvalue, eigenvectors like geometric and algebraic multiplicity. So in that case, you cannot diagonalize that matrix. So likewise, there are Wilkinson's matrix is also there, okay, and they are very, very. I have given you 2-3 matrices, Hilbert, Hadamard. Today I will give you Wilkinson's matrix. This is also very ill conditioned matrix. Got my point? These eigenvalues, these matrices are coming from application. It is not like that somebody has given. It looks very good, symmetric, positive, definite, diagonalizability, everything is there. But still it is difficult. Why? The eigenvalues are very close to each other. They are separated, but with very, 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 very close to each other. You know, with say 10 to the power 0. Up to 4 digit it is same, and next 1 or 2 digit it will differ like this. Okay, so that kind of eigenvalue are very dangerous. Okay, if you will search in the Google, good discretization is good vibration. If you are discretizing in the proper way and your vibration. In Germany, intercity train, you know, it runs around 350 kilometers per hour, is not it? Because they have developed some technique with this eigenvalue concept. Okay. So for minimizing the vibration, your discretization would be in the proper way. Understood? Today if you search in the Google, similarly in the Millennium Bridge, you might have listened this bridge, in London it is there. Engineers, they designed the bridge, okay. So after completion, after 1 or 2 days, so it collapsed, gir gaya. The reason was the frequency of the people traveling the okay, and the natural frequency, they matched, so collapsed. So the reason was the people, scientists, they search and they got a differential equation, and once a differential equation, if you do discretize, and then you will be getting the eigenvalue problem. Get my point? Because all this convergence, stability, all this of differential equation, it depends on the eigenvalue. If the differential equations are the coefficients of matrices, is not it? So if the coefficients are real or complex, then in that case you are getting some, you know already. If matrix coefficients, okay, if this matrix coefficients, then you have to get the matrix polynomial after discretizing, is not it? Say x dot equal to a x t, I told, e to the power lambda a, that is matrix equation, exponential e to the power. You can write the Taylor series expansion, all are the matrices, is not it? Yeah. And the professor is talking matrix equation, parameter dependent, all you have to play with the matrices, okay. But sometimes if the matrices are well conditioned, and things are easy to find out. But there are many applications now challenging, people are working hard problem, NP hard problem, they are difficult problem, understood? And those kind of problems you have to thoroughly, you have to understand what is running inside. And say people, what they are doing, if they have bigger problem, they transfer into smaller problem. Why? Because they don't have technique to solve the bigger problem, say non-linear equations. What they do, they transfer into linear, and they think that okay, we have done, because everything is available. Linear and non-linear transferring, everybody knows, formula is there, yes, is not it? That is what is the hard to do this, just transfer. And some linear problem, all techniques are available, you can solve that kind of problem. But transferring from non-linear to linear, you need lot of multiplication, lot of addition, lot of subtraction while transferring, is not it? When the bigger problem you transfer into smaller problem, you need lot of multiplications and lot of addition, subtractions. Say for example, if you are talking about the unit round of error, or it is in the floating point sense, if you do transfer, you are losing lots of data, understood? Even a small change, you have seen big change. So likewise, non-linear, if you are transferring, it's dangerous, but people doing research, getting paper. But if you put the ill-conditioned problem there, all this will collapse, won't work, understand me? So that's the challenge. So your theory should be computationally viable. If you are computational theory you are doing, you are computationally viable, it should be. Otherwise, just transferring, it will be. So here we will be seeing some examples on, yes, let's see, open. And all of you know this MATLAB, or how many of you know this MATLAB? All you know MATLAB, or are you using your, no? Acha, okay. So I will go from basic then. Okay, last class we discussed about some LU decomposition, correct? That you know, eh? You will just try at your home. If you have MATLAB, you just try. And you know plotting, how to plot the graph. No? And you got that eigenvalue? Did you calculate the eigenvalue? Did you try? Eigenvalue? Suppose you have this matrix, say I want to A equal to okay. Say you have matrix A equal to say R A N D random 5, okay. This 5 eigenvalue. This is your 5 by 5 random matrix, and you need to find, say I am finding eigenvalue E equal to EIG, okay, eigenvalue of a matrix. This is my eigenvalue, okay. Now you want to plot this. How will you plot this? The plot, you just command, give the plot command, okay, and you want to plot the real and the imaginary, real of this eigenvalue, real of E, okay, real of E, and the imaginary of E, okay. IMAG, this one E, and you just give some okay, okay. You give some real of E, imaginary of E. What's the problem? Oh, okay. This is comma would be there. But this line space x1, x2 and line, oh okay. For x1, y1 you will give the line space, plot of x1, y1, line space, y2, y2 and line space option. But it should calculate this plot real of E and imaginary of E, it is okay. So, anyway, if you plot the just you give the plot eigenvalue EIG of A, let us see what they are doing. This is the plot of eigenvalues and the real of the random matrix, this one. So, if you take some matrix like A equal to Hilbert, say 4 by 4, okay, and then you give this is, you also try from there if you know something, okay, you also try. It's taking time. Okay, here is a plot is there. Oh, here is plot. Okay. So earlier it was plotted. Let's see. The earlier one will see. Yeah, these are the eigenvalues. Okay, in the imaginary, real, and complex, whatever eigenvalues we have, these are the eigenvalues for the Hilbert matrix. Okay. Now we'll see as you go and increase the size of the matrix. Okay, because here is, say I am changing eigenvalue of A. So let's see. Okay, so I am giving here, say A equal to Hilbert 20 matrix, size is 20. Okay. Now you plot this real of so close, है the hill is 20 by 20, and these eigenvalues here very close to 0. They are very close to 0. So all they are merging here are here. This is 20 by 20 Hilbert matrix. Okay. Say if I will change this, say here is this you just give this format double, say format check here. Okay. Format long you can give. Yes. Of Hilbert, this is 50. Okay. 50 by 50 say. This is your. Now I want to plot this. What is happening here? This is eigenvalues. Can you imagine? Can you see this? Why this Hilbert matrix is the ill condition? Why Hilbert matrix is the ill condition? Because as I told you, there is 50 eigenvalues are there, and you are just seeing few eigenvalues. It means their eigenvalues are very close to each other, very close to each other. And this is format long is there. That means if you change it slightly to that particular matrix, its eigenvalues or its solution will get changed drastically. Okay. Say for example, here you have matrix A. A is a matrix. This is 1, 1, 0. Say this is 1. This is a matrix. This is called a defective matrix. This is called defective matrix. Okay. This matrix is defective. Defective means algebraic multiplicity of each of the eigenvalue lambda I strictly greater than geometric multiplicity gm of each lambda I. Say here lambda I is equal to 1, I varies from 1 to 2. Yes, correct or not? If all the eigenvalues of this algebraic lambda I is equal to geometric lambda I, then you matrix, then the matrix A is diagonalizable, is not it? Yes. Sometimes this diagonalizability condition we are trying for the whole numbers, say big number, separate, well separated, and these numbers, if they are very close to each other, they are very sensitive as well. Say for example, here is a matrix, this Hilbert matrix is also a simple matrix, maybe you can tell, you can see, just you see the eigenvalues of these matrices, just you calculate, okay, yes, you just find out the eigenvalues. These are the eigenvalues of the matrices, okay. I have taken in the format long, okay, and you can see the many eigenvalues are 0 as well. The size of the matrix is 50 by 50. Maybe if we will take further long, maybe some entries would be non-zero, okay. Some matrix, some entries might be non-zero, okay, but till this 2, 4, 6, 8, 10, 16 means, okay. But this matrix is symmetric and positive definite, is not it? Positive definite, and theory says all the eigenvalues should be non-zero. So, there must be non-zero eigenvalue, there must be non-zero eigenvalue, but this non-zero may be further, maybe you will give 50 space, maybe non-zero eigenvalue, they are distinct, but it seems this is 0 for the format long we are giving, we are getting a matrix. Understood my point? There are two things, one is numerically how this matrix looks, numerical sense, and up to what extent we are allowing this is 0, get my point, up to what extent we are allowing 0. But theory says this matrix is all the properties of symmetric and positive definite. Say for example, somebody is working theoretical, he will see this is correct, this is positive definite, all this condition of positive definiteness he can apply and he can do research. But computational point of view, if he will give some example or you draw, then drastically it will change, his theory won't work, got my point. So, for those kind of problems what people are doing, you are changing A plus delta A, say for example, this is defective or this kind of matrix, if you want to change this A plus D, and this delta A would be very, very small, very, very small, you will change this very, very small, and it is around unit round of error, say for example epsilon, okay, by looking this. Then you can study the behavior of this matrix A plus delta A, behavior of this kind of matrix, whether these eigenvalues are simple or it is defective, and all such cases you can study. So, if you make the bigger, you see, if I am making this, how can I be big this one? See, these are the x and y, okay. I can make it bigger, I can make it bigger, you just see, look this, how is changing, where is it gone? Yeah, this are, if I will make this, I want to make it little bigger. You might be seeing that every time you are getting some eigenvalue, you see, they are distinct, okay. Every time I am getting all these 50 eigenvalues, yes, you see, Okay. See, eigenvalues are there. Okay. So we can, okay, we can give this numbers here. So you can put the range, like if you are putting the range this, it is coming around 10 to the power minus 5 and 10 to the power minus 10. This is very, 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 very close to 0. That's why. But this, around this again you may have the 40 eigenvalues. Got my point? You cannot, it is very. And if you see the surface plot of it, surface plot, you what is the command for the surface plot? Yes, is this? Okay. Contour. So again you can check by putting this contour plot, contour of say you can see surface, or you can give the surface plot. Okay. Yes. What's the command for this? Can I put this? So like you can give here, okay. So you just put this mesh grid, x and y, whatever you have this, and then you can put surface of x, y, and this, okay, x, y, say copy, you can put here. Okay. Then you can put, say, you can change the range of this. But you have to find within the range. No, it is not taking. So directly it should come. Say for example, you want to plot this. So, you have to write a M file programming, otherwise it would be difficult. So, likewise you can just put this x and y, because already you got the eigenvalues, and just you find the range of x axis and the range of y axis, and you just put the x y. Okay, understood how you plot this? You just take the x y, you decide from the minimum eigenvalue and the maximum eigenvalue range. Okay, you just take x axis and the y axis. With that range you just plot, because eigenvalue you already have this, and you plot this surface x y z, and you will find how this Hilbert matrix is sensitive. Okay. Okay. So, next you have to, okay, like here you have here you see you go to the end of this. Like this. Say if you have this, and just you decide the you have to write a M file first, you just create a M file and give the matrix, like input the matrix A every time, and you find the eigenvalue of that matrix each time. Okay, and you just take the plot of real and imaginary. Here also you define the x axis and the y axis also, like you just generate the mesh grid, x y equal to mesh grid you give, that means you are making x axis and the y axis with the small interval. Okay, and with this mesh grid you would be calculating this eigenvalue of this matrix, then only you can see how close these eigenvalues are. Understood, my friend? You just create a M file, okay, and you just give this, and x and y axis you just define as I given you this one. Where is our MATLAB? Yes, like you give this one. So, first you give x and y axis, you just write this mesh, that means the x axis and the y axis you create, and with the range. Okay, and so once you created x y, then you have the eigenvalues, you forget about this, and you have this eigenvalues x and y you have, and then you plot with that. So, you will get this. So, use the axis eigenvalue visualization. How you will do? Use axis equal to maintain the aspect of ratio, use grid on for better clarity, use hold on to overlap plots, use different markers color for the multiple sets. Means to see the better way, you just use this axis, that x and y axis with this proper ratio. Like we have put the grid on, this we have plotted, and then you see how it is happening. So, as I told you that Hilbert matrices are symmetric and positive definite. Okay. Okay. and you just write a MATLAB code with different n, okay, and you check the eigenvalues of Hilbert matrix for different matrix size, like n equal to 10, 15, you just check this and you can see the behavior of the eigenvalues. Now, similar to that, you can also take one matrix called Wilkinson matrix. Not coming. Okay. Say for example, you are taking the Wilkinson matrix. Okay, this is Wilkinson, E equal to I of Wilkinson. This is another ill condition matrix, like Hadamard matrix and the Wilkinson matrix. And this matrix is symmetric and tridiagonal. This is symmetric and tridiagonal. Okay, tridiagonal, which is having 3 diagonals, super diagonal, main diagonal and subdiagonal. Eigenvalues are all real and nearly equal in magnitude. They are very nearly equal in magnitude, used for studying eigenvalue sensitivity and the clustering. They are very clustered, means they are very close to each other. This is another ill conditioned matrix, and looks this is very good matrix, but computationally it is very bad. Okay. Okay. So, similarly, you just compute the eigenvalue. You just write n equal to, you can write a m file. I have given n equal to 21. So, you just put n equal to 2, 3, 4 up to 20, say, or 30 or 40. You just take this and you compute the eigenvalue and plot the eigenvalues. Okay. These are again very ill conditioned matrix. Now, you will see this ill conditioning here in the MATLAB, if you have this. I will come with this. Where is command prompt? Where is MATLAB? Huh? Okay, I have to open this. Okay. Yes. No, it is not coming. Hanged. Yes. Okay. Yes. Now you just put the help Wilkinson. Okay. Now this is the Wilkinson's matrix. This is examples. This is the Wilkinson matrix. You can see this is a tridiagonal matrix. Okay. This is 7 by 7 matrix. Now you just check this eigenvalues. Say if I am giving E equal to, say I can put this how much this is Wilkinsonian. Acha. You just find this Ig of Wilkinson. So I am giving here 20. Okay. These are the eigenvalues, and same way you just plot this. What is the plot? You take this. You just put this ANS. Okay, that's the plot we need. Plot. This is the matrix, and where eigenvalues are very close to 0, you see, all the eigenvalues are lying here. It is a 20 byte, and there is a, you see, there is a overlapping. They are very, very close to each other, but the eigenvalues are distinct. Yes, as you have seen here, you see these are the eigenvalues. Okay, all eigenvalues are around this. This is very, you can see here, this is 0 to 0 3, and you just give the format long. Okay, you give the format long. And then you calculate the E equal to Ig of Wilkinson 20, say. Okay, E equal to Ig of Wilkinson 20. You see this matrix, you see, they are very, very, they are distinct, but very, very close to each other. They are very close to each other. See, this is 5.38941147, 5.3894, and changing from here 109209, something changing. Very similar. Huh? Yes, you see, all the eigenvalues are distinct. Yeah, yes, some jump is there. Jump again, they are clustering. Yes, because some eigenvalues looks very distinct. They are very separated, but some of these are very close to each other. So when they are very close to each other, so they are very sensitive. That my point. Say for example, you want to find the eigenvalues by using power method. The power method sometimes if their convergence is very slow, because they are linear. If you do divide one iterative to second, they are very linear. So if they are linear, convergence will be very slow, is not it? Say for example, their eigenvalues are very close to each other, 2.3578, 9, 10 divided by this, they are very, very linear. So, it won't converge, it won't never converge. And all these good algorithms, say for example, you have different techniques to find the eigenvalues and they won't converge, how you will find the eigenvalues? That's my point. Even if you have this QR algorithm, it says, generally what we do, if A equal to, A is a matrix and you need to find the eigenvalue by using QR algorithm. Okay. QR algorithm, what it says? Say A equal to, you have Q R. Okay. Say A naught, you just say set A equal to A naught or A naught equal to A. Okay. And then you are finding this eigenvalue, this A0, and you set this A1 equal to this reverse way, R0 and Q0. Okay. So, once you got Q0, R0, this is the Q0 is orthogonal matrix and R0 is upper triangular matrix, is not it? So, you just set, just do the reverse way. And again what we are doing, this A1 you got, then you'll find A2, then you make again that QR decomposition of this matrix, this say A Q1 R1. Okay. What you did? First you have computed this QR and you make in the reverse, just you are multiplying and this set as A1. Okay. Got my point? Now, once you got this, then again you make QR factorization of this matrix. Understood my point? Once you got this, you set in the reverse way and then you calculate the QR factorization of this matrix and that would Q1 and R1. Okay. And you can see this A2. Similarly, you just again set A3 equal to R1 Q1, okay, and then you find this A3, this A2 is Q1 R1 and you are getting this Q1 R1 you got, okay, Q2 R2. This is Q1 R1 and no, once you got this and then you have to get this A3 equal to, you make it to in the reverse way, R1 Q1. Okay. Now, A4 you make it this, you make a QR factorization of this, say Q2 R2 I got. So, likewise you will proceed. So, what will happen, you will see, if this matrix is there and suppose this is a matrix, you have this matrix, say, okay. So, again and again if you do, what will happen, that you will get this this entry, you can get this separate. But first of all, you make into either Hessenberg matrix, say any matrix, you make into Hessenberg form. Okay. The Hessenberg means this is like, this is the diagonal matrix, this is subdiagonal entries, and these are these, and this is 0. Below main diagonal, you have one diagonal entries. Right? So, first you will do make it to Hessenberg. Say I am making this, say it is a 4 by 4 matrix. This is this one. This you have 0. This one. So 0, 0. Okay. This say, and 0 0. Okay, this is 4 by 4, say for example. This is 4 by 4. This is Hessenberg matrix. This is one subdiagonal. This is main diagonal, and this all the integer. This is called Hessenberg matrix. Hessenberg matrix. So, why we are doing Hessenberg matrix for finding the eigenvalues? Because convergence should be faster. Convergence should be faster. So, here we are using QR factorization. Any matrix we can make into a Hessenberg by using similarity transformation, say Q transpose and Q. Understood my point? Every time what you are doing, you are making a similarity transformation. So, as you know that already, suppose a matrix is there. Suppose you have matrix A. This is matrix. What you will be doing? This is say 4 by 4 matrix is there. This we have matrix. Okay. So, what you are doing here? You are making a similarity transformation. How? Now, you want to make this entry to be equal to 0 to keep matrix as a Hessenberg form. Okay. And then you want to make this entry to be equal to 0. Okay. So, for this, if I will take this vector as a x, okay, then I can make this entry to be equal to 0. Okay. Like you remember, say x1, x2 and here q, then you would be getting some non-zero entry and 0. Yes, in our last class we have seen. Yes or no? Either it is a reflector or it is a rotator. So, similarly, here is a instead of taking whole x, you take this 3 entry, and then you form that u equal to x minus y, and what would be v? What would be v? If it is x minus y, v equal to, yeah, what is v? Vector v. Last class you have discussed. What is that? You remember, you can recall this theorem. Then for any x y, x not equal to y, norm of x equal to norm of y, there exists q such that q x equal to y. Yes or no? We discussed this in our previous classes. This is one theorem, and one corollary we discussed with that you just put this y equal to plus or minus norm of x to this is 0 all 0. Okay. And then what you got? This here x not equal to y, but norm of x equal to norm of y. Yes or no? Then there exists as this by this formula, then we can find q such that q x equal to y, and y look like x norm 2 and this is 0. Yes, this is our y, is not it? Yes. So, that means once you have this x and y, then you can always construct this one. So, from this matrix you can just take this as a x and you can get this matrix in the first transformation. You will get this one, say this is a star and this is 0 0. Okay. This is star, you have this, and this you have this one. And what you have done? You have multiplied one matrix here A and Q say 1 transpose. Okay. Got my point? So, to maintain the similarity transformation, so we will write in the right Q1, that is Q1, we will write this. So, that means once you got this Q1 transformation here, and if you do multiply, it will not change the entries of these entries. The 0 entries will not be disturbed. Okay. So, first similarity transformation you got, if you do multiply, again you will be getting Heisenberg form. And likewise, you can get this Q1 transpose A Q1, and similarly, you will get for the second column Q2 transpose, okay, and then again you will be getting what? This is star, this is 0 0, and this star star, this is star, here you will be getting 0, okay, and this should be remains same, okay, and this. For each column you need this, and for Heisenberg another one reflectors you need to make this entry to be equal to 0. Okay. So, what we have? This again Q3 transpose, Q1 transpose, this is Q2, Q3, Q2, and Q1 transpose A. This is this would be Q1, Q2, Q3. This would look like completely Heisenberg. Yes or no? This one, and this is 0, this star, this is 0 0, and this is star. This is what you have. This is now you this maintain the similarity transformation. Okay, and this you just take this Q as a Q transpose A Q, where Q equal to Q1, Q2, Q3. Okay. It means the left hand side is similar to this matrix, is not it? Because this is orthogonal transformation. This matrix is similar to the right hand side matrix. That means the eigenvalues of this matrix left hand side equal to eigenvalues of this matrix. Understood my point? So, first job is you have to do this for calculating the eigenvalue. Understood my point? First job is you are doing this similarity transformation by the help of QR factorization. Okay. QR factorization you know, and then what you will do? How it is happening? If you maintain the say QR algorithm to this matrix, not this matrix, because we need to find the eigenvalue. Either you find the eigenvalues of this or you find the eigenvalues of this, because this original matrix we have made into sparse matrix, yes, by using similarity transformation, and this Q matrix is a well stable algorithm. I told you by reflector you are good doing, this is very stable one. Okay. So, if you do multiply, you will be keeping that all these algorithm is in stable way. So, once you got this Hermitian Heisenberg form, so then you have to perform QR algorithm, what I did before. What I have done, first if you have a matrix, say this is a B matrix, now I am calculating with B not instead of A. Why? I have transferred this matrix into Heisenberg, and these matrices are similar. Eigenvalues of the left hand side A and the eigenvalues of the Heisenberg matrix. Yes. Any question? We have transferred similarity transformer. Similar matrices have same eigenvalue. So, eigenvalue of this B matrix. Now, I'll do this B equal to, say I'll put this B equal to now Q and R. I'll make the orthogonal matrix transformation. Q is orthogonal matrix and A. Now, what I'll do? This B1 set, okay. This would be like RQ1, R and Q. Okay, reverse way. Once I have calculated this, we have you should not do anything, just you make it reverse. Okay, you have said like this. Now, we will get this, you perform the QR factorization of this. Okay. Now I will get the another matrix, this is B2, say I am getting Q1 and R1, because I am making the QR factorization of it whole matrix, and that Q1 is orthogonal, R1 is. And similarly, set again another matrix, you will get this is B1, B2 and B3 say. What I will do? This is R1 reverse way. Okay, I will make it like this. I will make R1 Q1. Okay. So, once I will get this, then I will get the another matrix say B4, okay, like this. This would be Q2, because Q2, and this is R2. If you will do continuously until I will get this entries to be 0. What I am doing here is this, see, if I will do again and again, and there would be matrix here, okay, this 0, and this entry would be going near to 0. If I will perform again and again and again, this entry will go towards 0, and if you will go towards 0, then I will make this. Okay, understood my point? If this is 0, and this will be the eigenvalue, so I will extract it. Understood my point? If this is going to 0 up to this tolerance, whatever you have set in your computer or in your MATLAB, or how much desired accuracy you need. Once this equal to 0, then you have extracting this lambda 4 equal to got lambda 4. How it is? This is a block matrix. This is a block matrix. Eigenvalues of this block is the eigenvalues of this. Is not it? That means this is a 3 by 3 matrix. That means lambda of this eigenvalue, say for example, I am putting this H3 union lambda 4. Yes or no? Yes? Because this entry is 0 already. I can extract this. This is an eigenvalue, because block matrix. Block matrix, you have this. Say for example, I have matrix H4 equal to, this is my H3 and this is my lambda 4. This is 0, 0. Yes? Because this is H3 and this is lambda 4. So, I extracted one eigenvalue lambda 4. I got this lambda 4. Okay? Understood? So, I got one. Now, my matrix size is 3 by 3. This is Heisenberg matrix. So, again I will take this matrix, one eigenvalue I got, I can keep safe as it is, this got. Now, I have 3 by 3 matrix, this and this, and I have this one. Now, this is 1 0, this is my matrix, and say this is my B1, okay, and I will make it to this Q1 R1, okay. Again and again I will do until I get the tolerance, and by the way you will see this entry will be going towards 0. Got my point? And so, once I got this, then I will make this partition. So, now I got this lambda 4, okay, clear? Okay. And so, once I got this, my 2 by 2 matrix remain. So, once I have this 2 by 2 matrix, say B2, say I have this star star, this star. Again I will perform the QR algorithm like this previous one. So, once I will do this, then we will find that this would be equal to 0, near to 0. Okay. Once you got this eigenvalue, this eigenvalue. This you got lambda 3 and lambda 4. Got my point? What is the procedure? Yes or no? So, what you are doing is similarity transformation. So, you maintain the similarity transformation as long as you can. That means the eigenvalue will preserve. Okay? Because all the time we are maintaining the similarity transformation. But if you apply this algorithm to this kind of matrix, it would be problem. Why? Because the convergence would be slower. Why? Their eigenvalues are very close to each other. Okay? And if you take the relative error, is not it? What you are doing? Previous step, next step, just divide. If they are very close to each other, it is 1. Where it will converge? It will converge if the ratio is less than 1, very small than 1. Then you take to the power n, n goes to infinity, it is going to 0. Yes or no? If their eigenvalues are very close to each other, the ratio is 1. To the power n, you will go to infinity. Understood my point, what I am telling? Their eigenvalues are very close to each other. If I will take the ratio of it, one iteration to next iteration, if I do divide, and if I will see this would be 1, and this algorithm won't work. Understood my point, what I am telling? But in general, you can perform, you can find the eigenvalues of all the matrices, and all the day to day you have the well conditioned matrix very nicely you can get, and it would be very stable way to get this one. Understood? To overcome this kind of matrix, ill conditioned matrix, then we have again further different approach. It's called shifted QR algorithm. You know the power method. When you find the eigenvalue, instead of going x equal to lambda x, you are finding. Yeah, understood everybody? Or I will repeat again. Should I repeat? Huh? No? Got everybody? So all the time you are making a similarity transformation with the help of reflectors. Correct? Okay. I will give you some examples in my next class how this for this matrices. So, for example, you have this Ax equal to lambda x. Okay, this is eigenvalue problem. If I can use the shift operator, like if I will take a minus mu I, this x, this would be lambda minus mu x. If lambda is an eigenvalue, lambda minus mu is also eigenvalue of this one. So, if my eigenvalues are very close to each other, say lambda 1, lambda 2, lambda 3, lambda 4, and so on, my very close sometimes is there. So, what I will find? I will find some shift mu, maybe any number, a complex number you take, so that it will make well separated. Can I get this? I can get some here if they are very close, some of the eigenvalues, because in the Wilkinson matrices some of the eigenvalues are close, but some are far, is not. If they are very close to each other, so I can take some external number, if I make the difference, so I can make little separation. Okay, some case I can do, is not it? So can you think if two eigenvalues are here, lambda 2, lambda 3 are there, here is lambda 4, say here is lambda 4. So I can pick some number so that I can maintain this two well separated. Can we do this? Yes or no? Can you do? कर सकते क्या नहीं? Can we do this? If you have clustered eigenvalues are there, few eigenvalues, and we can take some complex number here far from, maybe some far from, or we can take in between near to this, and some eigenvalues would be separated and some eigenvalues again be closed. Shifted power method, have you learned? No? This is one eigenvalue, and if you have this, then you can make this well separate. This is called shifted power method. This is for the power method, and shifted QR algorithm you also algorithm. Okay. Shifted, and sometimes you have this, if eigenvalue of this, now you will work on this A mu I instead of A. I will make all this QR algorithm with this shifted matrix. Okay. So, first my target is to make it to Hessenberg form, then you make a mu I, and so once you do that, then you again you make the similarity transformation Q1 say transpose and the Q1 and so on. This finally you will get Q transpose Q, and this you will get some Hessenberg form, and Hessenberg form. Okay. This is 0, and this should be like this, and this you will get this. Okay. So, once you apply this again QR algorithm again and again, right? So, same way this entry will be going towards 0 and make this, you will get the eigenvalue. Say for example, I got some eigenvalue here, say if it is 4, this lambda 4 I got this. Okay. And then I can do again, and this lambda 3, lambda 2 and lambda 1. Okay. So, we have this, these are the eigenvalues of A minus mu I. These are the eigenvalue of A minus mu I. What would be the eigenvalues of A? These are the eigenvalue of this lambda, say this lambda 4, and this would be A equal to this mu plus lambda 4 into x. So, once after getting this, I will make this lambda 1 plus mu, whatever I subtracted before, you remember, mu I subtracted, and this would be the lambda 2 plus mu, and this would be lambda 3 plus mu, and this would be lambda 4 plus mu. Understood my point? See, I subtracted here, and then I performed the QR algorithm by reflector Hessenberg I form. Then I maintained the similarity transformation, got the Hessenberg. Now I got this matrix with the shifted. Then I will make the QR algorithm to this matrix. Instead of A, I am making to this. Okay. After that, I am getting here the eigenvalue. This eigenvalue of A minus mu I. Yes or no? Then the eigenvalue of A would be mu plus lambda 4. So, once you got this eigenvalue, you add it mu every time. Yes, doubt hai? No. You subtracted this. What is this? A minus mu I, you got the eigenvalue of this matrix. You got the eigenvalue of this matrix, means lambda 4. So, if I will get Ax equal to mu plus lambda, you subtracted, okay, from here matrix you subtracted, not eigenvalue subtracted. You subtracted with the matrix, because you have this property. If you are subtracting this, and the corresponding eigenvalue for this is this, but this is what? This is lambda 4. You know it. This is lambda 4. But what would be the lambda? Because lambda is an eigenvalue of this. Yes or no? This is equal to lambda minus mu, and this lambda equal to mu plus lambda 4. Understood my point? Because Ax equal to lambda x, A minus mu I x equal to lambda minus mu x. Clear? So, we can get this eigenvalue when the eigenvalues are very close to each other. But in some cases also it may not work, because there are many examples are there where this shift may not work. Understood my point? Then you will go for the inverse shift algorithm. What is that? This you understood? Now what we will do? Instead of that, say eigenvalues are very close to each other. First is inverse algorithm, you know this. Instead of this lambda 1, lambda 2, say lambda 3 are there. So what I'll do, I'll make into this say lambda 1 is the biggest element and this is the smallest. I'll do the reciprocal. So 1 by lambda 4, 1 by lambda 3, okay, 1 by lambda say 2 and so on. This is inverse I am doing. Why I am doing? If a lambda is an eigenvalue of A, lambda inverse would be the eigenvalue of A inverse. Yes or no? So what I will do? A inverse x equal to lambda inverse x. So here we are taking the matrices are non-singular. Correct? So I will perform the operation on this matrix on A inverse instead of A, because when the eigenvalues are very close to each other, if I will make the inverse, they will be well separated. Is not it? If they are close, I'll make the inverse, say 0.03 say. If I'll make the reciprocal, it would be 300. Yes or no? It would be bigger. So I need the bigger. When it is close to 0, it would be problem. So I made the inverse, and now I will do the A inverse. I got this matrix A inverse. I will make this this similarity transformation over A inverse. So say for example, this is my B matrix, and whatever I will get this eigenvalues, and then you make it inverse. Okay, you maintain the similarity transformation, and if you are getting the eigenvalue, this you are getting this entry, this is 0, and you are getting say this is lambda 4, and this lambda 4 you got the eigenvalue. That means eigenvalue of A inverse you got. Eigenvalue of lambda 4 you got the eigenvalue of A inverse. Now you just make the reciprocal lambda 4 1 by lambda 4, it will get the eigenvalue of A. So likewise you just make this by looking these eigenvalues, if they are very close to each other, make it inverse, and sometimes it inverse may not work. That is also there. There are many examples where like very ill conditioned matrix. See, I am talking about for all kinds of matrix. So all those methods are available, still the research is on. Again further ill conditioned matrix are coming, or the available algorithm may not work. So in that case you will go for inverse shifted power method. What will go? Inverse shifted power method. This is say for example A minus mu I, this is equal to lambda minus mu x, this is that, and in this case what will do? The A minus mu I inverse, this would be lambda minus mu inverse x. Yes or no? If x equal to lambda x, then A minus mu I x equal to lambda minus mu x, and I will make the inverse. That means inverse would be the eigenvalues of this A minus mu I. You know it? Clear? So what I will do? If I have this A minus mu I, you take inverse, this is B, and again you perform the QR algorithm to it. So whatever you will get the matrix, say for example 4 by 4, and this is 4 by 4. After this similarity transformation, you got the Hessenberg first, and then you have this are getting 0, and say for example you got this eigenvalue is lambda 4, and this lambda 4 is an eigenvalue of A minus mu I inverse. Is not it? That means A minus mu I inverse this x equal to the lambda 4 x. Yes or no? Then this is the eigenvalue. Then what you will get? A minus mu I, this x equal to 1 by lambda 4 x. Yes or no? And this from here I will get A x equal to 1 by lambda 4 plus mu. This would be x. So my eigenvalue would be like this. So eigenvalue of A would be 1 by lambda 4 plus mu. So you shifted, you have used, and then later on after getting this, then you are adding that shift. If you are taking its inverse, then again you make it inverse of that eigenvalue what you got, and you add that matrix. Yes or no? Any doubts, please? Because computing eigenvalues is the again challenging, you know, because finding the roots of the characteristic polynomial, it's challenge. Okay, it is not like that just you put in the MATLAB or you will get the eigenvalue. No, it is very, very difficult, because from the roots of the polynomial you will be getting a matrix, is not it? Companion polynomials, whatever you have. So in my last class, in my next class I'll show you with some example how this eigenvalues with shift, without shift, and how it converts. And many problems are there where the computing eigenvalues is the challenging and the difficult task. Say for example, this Wilkinson's matrix you have seen, and the Hilbert matrix and the Hadamard matrix, these are very ill conditioned matrix. Okay. Okay.
So,
Yeah, please.
sir, we are trying to find the eigenvalue with the help of Heisenberg matrix.
Yeah.
So, before applying the inverse shifted method, if V is not non-singular, like Heisenberg matrix is non-singular, then how we find B is equals to A inverse?
Because if your matrix is a non-singular,
Yes.
and it is similar to another matrix, so what would be the properties? It would be non-singular.
So B is also considered non-singular.
It cannot consider, it is by default. You see the proof. Say A and B are similar. A is S inverse Bs. Yes or no?
Yes.
So if A is non-singular, so B would be non-singular. Take the determinant. Determinant of S inverse, determinant of B, and determinant of S. Yes or no?
Yes.
So that means what? Determinant of A is equal to determinant of B. If this is non-zero, so this is non-zero. This is linear algebra. We are Heisenberg, we are getting by using the similarity transformation. We are not doing anything. See, left hand side we are multiplying orthogonal matrix, and the transpose itself is inverse. Is not it? Because we are maintaining the here is he may not be in orthogonal, and here we are doing A, this Q1 Q transpose and A Q. This means what? Q inverse A Q, and this we are getting Heisenberg matrix. Yes or no? Because similarity transform both sides we are multiplying. This is what we are getting, like exactly this. Yes. So obviously, if A is non-singular, A is non-singular. So we can apply whatever theory we have, the Heisenberg properties we have. So basically, we are using the QR algorithm again and again to get the matrix done. Yes, any other question? Yes or no? Understood? नहीं 50-50 क्या है? got how to find the eigenvalue in a stable way, because QR is stable. I have shown you, even for a badly ill conditioned matrix we are getting right result. So, similarity transformation we are using by using reflectors, not gram scheme. As I shown you that gram scheme sometimes it is very bad if we apply to ill conditioned matrix. Like we have seen Hilbert matrix, it is coming around 5 point something, very big error, I minus q transpose q. It should be equal to I, but instead of that the norm should be equal to 0, but in gram scheme we are getting some big number. Okay. And the modified gram scheme we are getting around 10 to the power minus 4, and for reflectors like Householder transformation we are getting around 10 to the power minus 15. So, very well stable method we are using, and if that stable method you will use to calculate the eigenvalue, and you get this. But there are still lot of challenges are there, lot of problems are there. There are shifts. Sometimes a single shift won't work, you have to take the double shift. Understood my point? Double shift. That means mu I have taken, then another shift you have to take gamma. Got my point? This is double shift, because double shift will be again faster than other, say very like this kind of ill conditioned matrix, they are very close to each other, and if you won't get answer you go for the double shift. And double shift, inverse double shift you can maintain, again some problems are there where it won't work, then again you have to go for the triple shift, then again you go for four shift, and you have for the multiple shift. In all the cases in shift we will be maintaining similarity transformation. And one thing, you can apply the QR algorithm to the direct matrix to get this eigenvalue, but it would be very costlier. So, that is why first you make that matrix into Hessenberg, like we did a matrix to upper triangular matrix, and then you get. Now, you can ask questions, so why we are not making upper triangular matrix instead of Hessenberg? You cannot. You have to make this Hessenberg form. So, Hessenberg form, the property is that just next to the main last entries it would make 0 towards. If it will make 0, then the last entry would be the eigenvalue, you extract it. You can find that eigenvalues. Then again the size of the matrix is n minus 1 by n minus 1. Okay. And again you perform this, but only thing is that when you will be using single shift, double shift, triple shift, multiple shift. So, your problem is you are getting some problem, you are not getting convergence, like they are very close to each other, but convergence will be linear, because very close to each other. Convergence is lambda 2 divided by lambda n to the power n goes to infinity, even you take 10,000 years it will not converge, is not it? They are very close to 1, they are very close, 0.003, 0.0034, close one, never converge, it will never converge. That my point.
Sir, sometimes we just need the most significant eigenvalues or stuff. In that case, we don't need. In many applications, we need majorly the largest or the least thing.
Yes. When a selected eigenvalue you want, yes, if you want selected eigenvalue, say for example, how many eigenvalues you need to find, say for example, power method is there, power method gives you the largest eigenvalue, that is the work is over, this is one. And sometimes what you do, instead of this largest eigenvalue, I need also some other eigenvalues, your question is, when at a time you need some eigenvalues which you want, not all the eigenvalues. Yes, you can find those eigenvalues because here is that here at least we are going from down. Okay, now from down you are getting this eigenvalues 1, 2, 3, 4, 5, 6, 7, and in that case sometimes it is also challenging to work on this. Say for example, some applications like it is called inverse eigenvalue problem. What it say? They don't want all the eigenvalues. Okay, they want some selected eigenvalues. Understood? Suppose n by n matrix is there, n eigenvalues are there. I don't want you don't want n unnecessary. Why you want the one I need for my application, that much that much. Say for example, we are doing this inverse eigenvalue problem. Say these are say complex number. Say these are not eigenvalue, these are complex numbers. Say lambda r. Okay, and other eigenvalues lambda n we don't require, lambda r plus 1. Okay, these are say these are expected eigenvalue. We need. We don't require this other eigenvalue because. So what do we have? This is approximate eigenvalue. Say ax equal to, say this is approximately equal to lambda I xi. This is not exact eigenvalue. This is approximate eigenvalue. Say, and these are the complex number, not eigenvalue. Okay. So what we can find? This is what we have. Now we can apply some small change to this matrix suitably. Okay, we'll change this matrix delta A. Okay, and this matrix, this would be the exact eigenvalue of lambda I xi.
Stability.
Backward stability. Okay, understood my point. I need the selected numbers to be the eigenvalue. Okay, so then I can make suitable perturbation here, delta A. I can find delta A. Delta A I can find some small change to this matrix, where this complex numbers, okay, and their corresponding approximate eigenvectors becomes the exact eigenvalue and exact eigenvector of this change matrix. समझ में आया ना क्या बात? So in this way, there are many people are working, and we have also some research problems we have done that how this selected eigenvalue we can construct.
Comment on the generalized eigenvalue problem and how can we convert it to regular eigenvalue problem?
Yes, the generalized eigenvalue, say for example, similar theory it can work, but not always. Okay, say for example, generalized, you mean generalized eigenvalue problem? Okay. Yeah, yes, Ax equal to say lambda Bx you have. Okay. This is also eigenvalue problem. So if B is identity matrix, then you have Ax equal to lambda Ix. Yes or no? This is lambda x. But in general, B say not equal to identity. Yes, B is not equal to identity. If B equal to identity, then Ax equal to lambda x. Okay. So in this case, Ax equal to lambda Bx. One case is if B is non-singular, then what we'll do? We can make it B inverse Ax equal to lambda x. Yes or no? And this is my Cx equal to lambda x. Yes. So I have transferred this problem, generalized eigenvalue problem, to standard eigenvalue problem. That is Cx equal to lambda x or C equal to B inverse A. But in general, B not non-singular. Okay. Even if B is non-singular and if you do transfer into this, but some problem in stability or accuracy and lot of things would be there. As I told you that if some problem, if you convert into linearization or you do, and you are losing lot of error. We are putting lot of errors, is not it? Lot of multiplication would be there. Say if I do multiply E C inverse B inverse A, I will be doing lot of multiplication, lot of addition, lot of this. But if the matrices are very ill conditioned, they are ill conditioned matrix. So in that sense, it would be dangerous.
But what if B is not invertible?
Yeah, that's yeah.
Not invertible in general.
Yes, general.
Then we will have no.
No, even if matrix is non-singular, you cannot make this.
What if B is singular?
Yeah, I am coming to that. I am coming to that point. I am telling, if it is non-singular, you cannot do this. If your problem is ill conditioned, understood my point? They again dangerous. You know that even determinant we cannot find, because lot of multiplication in the linear algebra sense, computational point of view, finding determinant is bad practice. Okay. So this is one way, and we avoid this sometimes. Okay. So we do what? Now Ax equal to lambda Bx. And here there are lot of development in the basics of linear algebra technique, but it is not as standard eigenvalue problem. There are theory, like diagonalizability condition, like canonical form, Jordan canonical form, all these things are there. And other cases, if B is, determinant of B is say equal to 0, this is singular. And if it is singular, you cannot take the inverse of this matrix, you have to take Ax equal to lambda, Ax equal to lambda Bx as usual, and you apply the theory for this. So same way you just find out, if you want to take the selected eigenvalue, you find the double perturbation, delta x, this would be say, if it is approximately equal to this lambda I, this is Ax I equal to lambda I Bxi, if it is that, then this is approximately equal to this, then you find the delta A and delta B, this xi which would be equal to lambda I B plus delta B. Okay. Sometimes if you want only one matrix to be perturbed, you can keep silence as it is. So there are two ways you can find. It depends on the application. First A plus delta A, xi, this is lambda I B xi. You can keep like this. For what value of delta A, this approximate eigenpairs becomes exact eigenpair. Okay. This is one way. Also you can find both the matrix A plus delta A, and this is xi equal to lambda I B plus delta B xi. Yes, sir. So both the way you can find, and you can find the error. This is what the backward error the epsilon, this is norm of delta A square and plus delta B norm square. This is your error term will be coming. This is say for example delta L. Okay, this is I am giving this norm, and this delta L, this should be in the epsilon neighborhood. All such delta L you choose which varying in the epsilon neighborhood if the matrices are ill conditioned. Apart from that, because in the epsilon neighborhood you have to thinking what the things are running, because the eigenvalues are very close to each other. Understand my point? Because these are very close to each other. So your perturbation would be very close to in the epsilon neighborhood. If the eigenvalues are very epsilon neighborhood, so your perturbation should be in the epsilon neighborhood. Otherwise it would be again dangerous. That's my point. क्वेश्चन बोलो, समझ में आया? थोड़ा थोड़ा, but keep trying, you will get this. This is the time to, है ना? It is not like that at a time you will learn everything. So things go slowly, research goes slowly. if, but again more Penrose inverse if you take again, you have you are calculating lot of things on that, you are multiplying more Penrose inverse. There is a singular matrix also. This matrix is called, this kind of matrix is called matrix pencil, A minus lambda B, okay, called matrix pencil. Matrix, why it is called matrix pencil, this is also not known, matrix pencil, okay. And this AB can be square matrix, can be rectangular. If it is a rectangular matrix, so it's all this inverse, lot of things, generalized inverse. Also we have the singular value decomposition for this double matrix, it is called a generalized singular value decomposition. Generalized singular value decomposition. If you put in the Google, say SVD, you know SVD for the single matrix, for the single matrix A, and for the pair matrix A comma B, sometimes we write A comma B instead of A minus lambda B, that called sometimes this is pair of matrix, okay. And if you find the SVD of, it's called a GSVD, and if you put in the Google, lot of things you will get. What is the singular value decomposition from the double matrix? Not only for this, you can go for quadratic matrix. Say for example, this is linear matrix, okay. This is this is linear matrix, say A minus lambda B is this is matrix is called linear. This is linear because linear in the lambda. And also you have the A0 plus lambda A1 plus lambda square A2. This is quadratic. Quadratic. Again, the linear algebra technique is being developed, but it is not as similar to standard and it is generalized. Again, things are more complicated. Okay, this is called a quadratic polynomial, and again you can extend it to the matrix polynomial. This is lambda I, I varies from 0 to n. This x equal to 0. Okay. This is also eigenvalue problem, is not it? Because you see, if I equal to n equal to 2, you will get this, and this is also eigenvalue problem. Just you put this is, and if you put this n equal to 1, you will get this A minus lambda I x equal to 0, that is A0. This is the standard eigenvalue problem, the one we discuss SVD or eigenvalue, and this is the linear, and you put A0 minus or plus, that doesn't matter, minus or plus, lambda A1 x equal to 0. This is what we got this, instead of BA1, and same thing you just in the bracket you put this one. This is also eigenvalue problem. In general, we are getting L lambda x equal to 0. This is L lambda is a matrix polynomial. So there are a lot of big applications in the control, vibration, people are working, and there are many applications. Instead of eigenvalue problem of standard matrix, people are thinking about double matrix, triple matrix, and so on. And there are also nice algorithm for finding the eigenvalue. Even if you put in the MATLAB, just you put eigenvalue of AB. If you just put AB and put I of A comma B, you will get the eigenvalue. Just you check. So you are putting A equal to, say I am putting R A N D, I of say 5, and B you put R A N D 5, okay, and you just find E I G of A comma B, A comma B. These are the eigenvalues. Even for the generalized eigenvalue problem, you have the MATLAB things are there, how to find the eigenvalues, how to find the eigenvectors, how you find the generalized eigenvalues, how you find the generalized singular values, generalized singular vectors, left vectors and right eigenvectors. All these things are available in the MATLAB. Not only for the double matrix, but for the polynomial also you can find all the information. Got my point? So, if we have learned everything in the linear algebra is based on the single matrix and operator. And if you want to more little bit further, you read double matrix. What is the characteristic? What is the diagonalizability condition? What is the canonical form? Like Jordan canonical for the single matrix you have, is not it? Now you think about the Jordan canonical form for the double matrix. But in double matrix you may have infinity eigenvalue. Okay, you may have the infinity eigenvalue also. Say, so what we are getting, suppose A minus lambda I is there, okay, and you find the determinant of this. What you will get? You will get a polynomial of degree n if the size of the matrix is n by n, is it? But in double matrix, so if you find the determinant of A minus lambda b and this is equal to 0, if b is singular, in that case you won't get this polynomial of degree n. That is the problem. Understood my point? If it is n by n matrix, okay, characteristic polynomial of degree n, and it has at most n roots, everybody knows. But in this case, if b is singular, okay, and you won't get the polynomial of degree n, you will get at least may less. So in that case, say for example, you are getting, say, if I will take this 1 0, say okay, 0 1 1 0, say my A matrix is there, and let B equal to 1 0 0. So in theory, what do you expect? Determinant of A minus lambda b. Yes, what would be this? 0, tell me, this would be minus lambda. What would be? This would be 1. What would be 1? And this? Minus? Minus 0, okay. This is, but here is 0 you are getting. That means you won't be getting any polynomial, okay. And if you change a little slightly, okay, you just take 0 and here is 1, what you are getting? What you will get? This would be 0 and this would be minus lambda and this would be 1 and this 0. So in this case what you got? The polynomial minus lambda, but degree is 2. So polynomial should be at least degree 2. We are missing. But in this case, size of the matrix means degree of the polynomial. Yes or no? This is one example. You can think, where is the problem? The general characteristic it won't follow. It means it has a infinity eigenvalue. The remaining one, the missing one eigenvalue 0 is there and another eigenvalue which one is missed, you cannot get here, that is called infinity eigenvalue. That means your eigenvalues are in the extended complex plane. Okay, in extended complex plane, that means complex plus infinity. So all this extended complex plane you can project into the sphere, stereographic projection. You can take, come back, go, come back, and your eigenvalues would be in the Riemann sphere sometimes. So that problem we can also think about like this alpha A minus beta B, okay, beta B, this x equal to 0. So this is called homogeneous matrix pencil, where here in this case if you find the determinant, your degree won't miss. will same degree. If it is 2 by 2 matrix, you have the polynomial of degree 2, because lambda and beta, alpha and beta would be there, because here beta lambda equal to, say this is beta by alpha, because if you put this alpha not equal to 0, then a minus beta by alpha, this is b x equal to 0, and this beta equal to lambda. Correct? So likewise, there are many things you can do. I think our time is going up. Huh? So likewise, you can find lot of things. There are lot of things to do the research. Okay. So thank you very much. If you have any further question, let's know. Yeah, please.
So finally, can we just conclude, like for a given a matrix, if we know that the eigenvalues are close to each other, can we conclude that it is ill conditioned? Like, is that a sufficient condition, or is that?
Yeah, if they are very close to each other, obviously they would be they would be ill conditioned. Why I have mentioned this? Because why it is if a matrix is very ill conditioned, if you say I have told you Ax equal to lambda Bx, okay, and if it is small change in the matrix A, it is drastically changing the solution. That already I gave many examples I have given. That is enough that it is going very far from this. And same way, eigenvalue concept, if the matrix is ill conditioned, and say my matrix is ill conditioned in the sense, if it is a simple, that means all the eigenvalues are distinct, but they are very close to each other. As you have seen in the Hilbert and the Wilkinson matrix, the eigenvalues are very close to 0. You have seen clustering, they are clustering. That means you have to do this analysis in the epsilon neighborhood concept. Otherwise, you cannot find the where you are going. Understood my point? You have, if they are very close to each other, you have your perturbation or your sensitivity analysis would be in the epsilon neighborhood. That very eigenvalues are very close to each other, that means it is ill conditioned.
In the generalized eigenvalue, how did you conclude that infinity would be the other eigenvalue?
Yes, because what you have this, say this is one, what I wrote, A equal to 1, क्या लिखा था, 0 1 1 0, and B was 0 1 0 0, है ना. अभी इसमें अप्लाई करो अल्फा ए माइनस बीटा बी, ठीक है. डिटर्मिनेंट क्या मिलेगा बताओ. दिस इज इक्वल टू, बताओ, this would be 0 alpha 0, and this is minus beta, this is 0 beta and 0 0. Yes, this is, and now determinant. So determinant of this is what? This is 0, this is alpha minus beta. Yes, and what would be this? This would be alpha and 0. Yes or no? Yes. And what you are getting here? If you do make determinant equal to 0, then you would be getting minus alpha minus beta equal to 0. अभी देखो यहाँ पे डिग्री 2 है ना, डिग्री 2 है ना. तो हम लोग का जो स्टैंडर्ड आइगन वैल्यू जो कंसेप्ट था, वॉट एवर वी गॉट दैट इफ द साइज ऑफ द मैट्रिक्स इज n, it's a characteristic polynomial of degree n. Okay, that means it has n roots. So if you do write in this form, alpha and beta, we will be getting here, we will be getting the two eigenvalues. What? The first one is alpha equal to 0, or this is alpha equal to beta, is not it? If not equal to 0, then alpha equal to beta, okay, and this is not alpha equal to 0. So we will be getting, and this pair is look like how much? This is alpha comma beta. So you tell me, if alpha equal to 0, one is alpha equal to 0, then alpha may not be equal to beta, so beta you keep it, and say alpha not equal to 0, tick alpha, alpha not equal, alpha equal to beta, so you take alpha. So what you got? Here you got beta times 1 0 and here alpha times 1 1. Yes sir. So that means what you got this. Your eigenvalues are 1 comma 0 and it's 1 comma 1. Yes or no? Because this is scalar multiple alpha. Because why? In case of alpha A minus beta B x equal to 0, if you do scale also eigenvalue, is not it? If you scale, because both the sides are, but in case of standard eigenvalue it won't, because this is 1 0 and 0. Or if you think in the extended complex plane, if you because our definition was beta by alpha, and if you do beta by alpha, here will be infinity, beta by alpha. So or alpha by beta. In other way, you just switch, it will be sometimes 0 comma 1 also there. Or you take this, that infinity eigenvalue would be coming, okay? And here 1 comma 1 is there. And then if it is in the extended complex plane, so you make the stereographic projection and you get the point in the Riemann sphere also. So infinity eigenvalue would be there if B is singular. But the polynomial of degree 2, if you are taking in the homogeneous form, because this is homogeneous equation, this is alpha and beta. Homogeneous, why? The degree are same. Understood, my friend? And similarly for the quadratic eigenvalue problem also same thing will happen. If I have this, say A0 plus say lambda A1 plus lambda square A2, this is, and this one say x equal to 0, and this if determinant of A2 if it is equal to 0, and I will get the infinity eigenvalue. If leading coefficient matrix is singular, always I will get the infinity eigenvalue. Okay, likewise. So in that case also you can make into homogeneous form and you will get this. The eigenvalue would be, so what would be the eigenvalue? Eigenvalue of this quadratic polynomial would be nm. Nm in the sense the size of the matrix is say n and degree is m, so eigenvalues would be nm. Understood? Because in quadratic polynomial for the standard case m equal to 1, because linear, that is why we are getting always n eigenvalues. If it is quadratic, that means degree 2 m equal to 2, 2n eigenvalue. If degree 3, 3n eigenvalue. If degree 4, if degree m, mn eigenvalue. Just you go and check in the MATLAB, you will get all the information. Okay, at least you should to know, you can search in the Google, you can find. Any other question? So now your linear algebra is extended to bigger linear algebra. So you can think in that way if you can contribute something, because people are working on that. Okay, thank you so much.